Look up at the stars tonight, and you're not just seeing distant points of light. You're staring into a cosmic puzzle that has captivated humanity for millennia. What if I told you that everything we think we know about the universe is just the tip of the iceberg? Beyond the familiar constellations and swirling galaxies lie mysteries so profound, they challenge the very fabric of reality itself. Welcome to an exploration of 46 horizons of discovery in outer space, where each revelation peels back another layer of the universe's grand design. This isn't just about distant stars or alien worlds. It's about the unanswered questions that keep scientists awake at night, the phenomena that defy explanation, and the discoveries that could rewrite everything we thought we knew. Consider this: every time we point a telescope deeper into space, we're not just collecting data, we're uncovering stories written in the language of light and gravity. Some of these stories hint at forces we can't yet comprehend, like black holes that warp time itself or cosmic signals with no clear origin. Others reveal possibilities that stretch the imagination, from hidden dimensions to ancient galaxies that shouldn't exist. These aren't just scientific curiosities, they're clues to understanding our place in the cosmos. Why does any of this matter? Because each discovery is a thread in the tapestry of human exploration, a reminder that the universe is far stranger, far more wondrous than we ever dared to dream. So let's embark on this journey together. Picture yourself standing at the edge of the unknown, where every answer leads to new questions and every horizon promises something extraordinary. Over the next 46 revelations, we'll traverse the cutting edge of astronomy, physics, and sheer human curiosity. You'll encounter phenomena that defy logic, theories that border on science fiction, and breakthroughs that could change our future among the stars. This isn't just a tour of the cosmos, it's an invitation to see the universe with fresh eyes, to wonder, to question, and to marvel at the infinite possibilities waiting to be uncovered. Ready to begin, the cosmos has been waiting. Imagine holding a snow globe, except instead of water and glitter, it's filled with galaxies swirling in perfect harmony. Now shake it violently. According to everything we know about gravity, those galaxies should fly apart, but they don't. Something invisible, something we can't see or touch, holds them together like cosmic glue. That's the enigma of dark matter. It's the universe's hidden architect, shaping galaxies with its gravitational pull, while remaining utterly invisible to our telescopes. Think about that for a moment. Nearly a third of everything in existence is made of a substance that doesn't emit light, reflect light, or interact with ordinary matter in any way we can directly observe. It's like trying to study a ghost by watching how it moves furniture. Scientists first stumbled upon this mystery in the 1930s when astronomer Fritz Zwicky noticed galaxies in the Coma cluster were moving too fast to be held together by visible matter alone. Fast forward to today, and we've mapped dark matter's fingerprints across the cosmos, from the way it bends light around galaxy clusters to the tiny temperature fluctuations in the afterglow of the Big Bang. Yet, despite decades of searching, we still don't know what it actually is. Some theories suggest it's made of exotic particles like WIMP, weakly interacting massive particles that barely interact with normal matter. Others wonder if we've misunderstood gravity itself, and that dark matter isn't a substance at all but a sign that Einstein's equations need revising. The hunt for answers is anything but passive. Underground labs shielded from cosmic rays search for rare particle collisions. The Large Hadron Collider smashes protons together at nearly the speed of light, hoping to create dark matter in miniature explosions. Meanwhile, telescopes like the James Webb peer into the cosmic dawn, tracing how dark matter's gravitational scaffolding guided the formation of the first galaxies. Every experiment, every observation is a piece of the puzzle, but the full picture remains maddeningly out of reach. What makes this mystery so thrilling isn't just the scientific challenge, it's the realization that the universe is far stranger than we imagined. Dark matter isn't some minor detail, it's the hidden backbone of reality, and unlocking its secrets could rewrite the rules of physics as we know them. Picture a cosmic river not of water, but of galaxies, all streaming toward some unseen destination like leaves caught in a galactic current. This is the Great Attractor, one of the most baffling gravitational mysteries in our universe. Located roughly 250 million light-years away in the direction of the constellations Centaurus and Norma, it exerts a pull so powerful that our entire Milky Way, along with thousands of other galaxies, is racing toward it at over 2 million kilometers per hour. And yet, we can't see what's pulling us. The culprit lies hidden behind the Milky Way's own thick band of stars, dust, and gas, a region astronomers call the zone of avoidance because it obscures nearly 20% of the sky from our view. For decades, this cosmic blind spot kept the Great Attractor's true nature shrouded in mystery. Early observations in the 1970s and 80s revealed galaxies moving far faster than expected, as if drawn by an immense gravitational anchor. At first, scientists thought it might be a colossal cluster of galaxies, but the numbers didn't add up. The visible mass wasn't nearly enough to explain the staggering pull. Some even speculated about exotic possibilities, like a concentration of dark matter so dense it warps the fabric of spacetime itself. The truth, as we're starting to uncover, might be even stranger. Recent breakthroughs suggest the Great Attractor isn't a single object but part of something far grander. The Laniakea supercluster, a web-like structure spanning 500 million light-years, with our Milky Way residing on its outskirts like a suburban neighborhood on the edge of a metropolis. Within this vast cosmic network, galaxies flow along gravitational highways toward dense hubs, much like rivers converging into a delta. The Great Attractor appears to be one of these hubs, but it's not the end of the journey. Beyond it lies an even more massive gravitational anomaly known as the Shapley supercluster, which might be the ultimate destination of this cosmic migration. The real puzzle isn't just what the Great Attractor is, it's why our current models of universal expansion struggle to explain its sheer gravitational influence. According to conventional cosmology, galaxies should be drifting apart as the universe expands, not flocking toward specific points with such coordinated motion. Could this be a hint of unknown physics, a flaw in our understanding of gravity, or evidence of large-scale structures we've only begun to map? Telescopes like the Square Kilometre Array and the James Webb Space Telescope are now peering through the zone of avoidance, using infrared and radio waves to cut through the cosmic fog. What they find could reshape our cosmic address and our understanding of how the universe organizes itself on the grandest scales. What makes this mystery so compelling is the humbling reminder that even as we map the cosmos in ever greater detail, the universe still holds colossal secrets just out of view. The Great Attractor isn't just pulling galaxies, it's pulling us toward a deeper question. How much of the universe's story remains hidden, waiting to be uncovered? One moment the cosmos is silent, the next an invisible beam of energy streaks across the universe, a flash so intense it outshines entire galaxies, lasting barely the blink of an eye. These are fast radio bursts, some of the most explosive and mysterious signals ever detected. In just a few milliseconds, a single burst can unleash as much energy as the sun produces in 80 years. Yet despite their staggering power, we still don't know what creates them. The first fast radio burst was discovered in 2007, buried in archived data from a radio telescope in Australia. At first, astronomers debated whether it was even real, perhaps a glitch or a stray signal from Earth. But then more bursts appeared, each one a fleeting, high-energy pulse from deep space. Some seemed random, while others repeated in unpredictable patterns, like a cosmic heartbeat. The fact that these bursts could repeat at all shattered early theories. Colliding neutron stars or evaporating black holes couldn't explain signals that kept coming back. One leading suspect, magnetars neutron stars with magnetic fields so strong they could strip the electrons from atoms halfway across the galaxy. In 2020, astronomers finally caught a fast radio burst originating from a magnetar within our own Milky Way, a smoking gun that at least some bursts stem from these extreme stellar remnants. But here's the twist: most bursts come from billions of light years away, far beyond our galaxy, and their energies dwarf anything a magnetar should produce. Could there be multiple origins, some natural, some still unexplained? The plot thickens with the discovery of repeating bursts that follow intricate patterns. Some arrive in precise intervals, suggesting an orbital dance around a massive object like a black hole. Others exhibit strange down-drifting frequencies, as if the signal is being stretched or filtered on its journey through space. Then there's the elephant in the room. Could some of these bursts be artificial? The idea isn't as far-fetched as it sounds. In fact, the Breakthrough Listen project has scanned repeating bursts for signs of encoded information, though no evidence of extraterrestrial engineering has surfaced yet. What makes fast radio bursts so fascinating isn't just their mystery, but their potential. Like cosmic lighthouses, their pulses carry imprints of the intergalactic medium they've traveled through, allowing scientists to map the universe's hidden matter. New telescopes like the CHIME Array in Canada are detecting dozens of bursts monthly, each one a clue. Whether they're natural cosmic fireworks or something more, one thing's certain: every burst we detect is rewriting the rules of high-energy astrophysics, proving once again that the universe is far stranger than we ever imagined. The universe is unimaginably vast, trillions of stars, each with planets orbiting in the Goldilocks zone where liquid water could exist. Statistically, we shouldn't be alone. And yet, when we listen, all we hear is silence. This is the Fermi Paradox, a puzzle that haunts astronomers and philosophers alike. If life is so likely, where is everybody? Named after physicist Enrico Fermi, who famously asked, "Where are they?" during a casual lunch conversation in 1950, this paradox has spawned decades of speculation, from the unsettling to the downright bizarre. One explanation is simple yet chilling: advanced civilizations might inevitably destroy themselves. Imagine a species harnessing the power of stars, only to succumb to war, climate collapse, or rogue artificial intelligence. This great filter theory suggests that somewhere between microbial life and interstellar expansion, there's a barrier so deadly that almost no civilization survives it. The terrifying question isn't just whether we've already passed this filter, it's whether it still lies ahead of us. Alternatively, maybe we're looking in the wrong way. Our searches focus on radio signals, but what if advanced beings communicate through neutrino beams, quantum entanglement, or something we haven't even imagined? Then there are the wilder ideas. The zoo hypothesis proposes that extraterrestrials deliberately avoid contact, observing us like animals in a cosmic wildlife preserve. Or perhaps we're living in a simulation, and the universe's apparent emptiness is simply a programmed backdrop. Some scientists even speculate that intelligent life might transcend physical form, uploading their consciousness into digital realms or higher dimensions, leaving no trace for our telescopes to detect. Projects like SETI and Breakthrough continue scanning the skies, analyzing millions of radio frequencies for patterns that defy natural explanation. Meanwhile, new tools like the James Webb Space Telescope are hunting for biosignatures, chemical imbalances in exoplanet atmospheres that could hint at life. But the silence persists, pushing us to confront uncomfortable possibilities. Maybe life is rarer than we think. Maybe intelligence is a fleeting spark in the cosmic dark. Or maybe, just maybe, we're the first to reach this stage, destined to become the ancient civilization future species wonder about. The Fermi Paradox isn't just a question about aliens, it's a mirror, forcing us to reflect on humanity's fragility, ingenuity, and place in the grandest story of all. In the endless tapestry of the cosmos, not all planets play by the rules. Picture a world untethered from any star. No sunrise, no sunset, just perpetual darkness as it drifts through the interstellar void. These are rogue planets, cosmic nomads that wander the galaxy alone, and they might be far more common than we ever imagined. Current estimates suggest billions, perhaps even trillions, of these solitary worlds could exist in the Milky Way, silently outnumbering stars themselves. Their very existence challenges our traditional notions of what a planet can be and where life might take root. How does a planet end up adrift? Some are violent castaways ejected from their home solar systems during the chaotic gravitational tug-of-war of their youth. When multiple planets form close together, their orbits can become unstable, flinging one or more into the abyss like a cosmic game of pinball. Others might never have known a star at all, forming instead from collapsing gas clouds too small to ignite nuclear fusion, becoming planetary mass orphans from birth. The process isn't rare. Simulations show a typical solar system could lose several planets this way, scattering them into the galactic wilderness. Detecting these dark wanderers is a feat of astronomical ingenuity. Without a star's light to illuminate them, rogue planets are nearly invisible, but they betray their presence through gravity. Using a technique called microlensing, astronomers watch for the subtle way these worlds bend and magnify the light of distant stars as they pass in front of them. It's like spotting a lens hidden in complete darkness by the way it distorts the glow of a faraway lamp. Already, missions like the optical gravitational lensing experiment have uncovered dozens of candidates, some as small as Earth, others giants many times Jupiter's mass. The most tantalizing question isn't just how they form, but whether they could harbor life. At first glance, a starless planet seems inhospitable, a frozen wasteland where temperatures hover near absolute zero. But dig deeper and possibilities emerge. Tidal forces from a planet's own moons, radioactive decay in its core, or even thick insulating atmospheres could trap enough heat to maintain subsurface oceans. Imagine an icy shell shielding a global sea warmed by geothermal vents, not unlike the hidden oceans of Europa or Enceladus, except this one floats freely between the stars. Such environments could persist for billions of years, offering stable refuges for microbial life, or even more complex organisms adapted to eternal darkness. The hunt for these elusive worlds is about to leap forward. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2000s, will scan the galactic core for microlensing events with unprecedented precision. It could uncover thousands of rogue planets, mapping their distribution and even identifying those with atmospheres, a crucial step in assessing their habitability. Meanwhile, next-generation telescopes like the European Extremely Large Telescope might one day directly image nearby rogue planets using advanced coronagraphs to block out starlight, revealing their composition and weather patterns. What makes rogue planets so captivating isn't just their mystery, but their defiance of expectations. They remind us that planets don't need stars to exist. and that life, if it's resourceful enough, might find a way in the most unexpected places. As we uncover more of these galactic drifters, we're not just expanding our catalogue of worlds, we're reimagining the very boundaries of where life could thrive in the universe. The darkness between stars may not be so empty after all. It could be teeming with hidden worlds, each carrying secrets of formation, survival, and perhaps even the building blocks of life itself. Late one summer night in 1977, a radio telescope in Ohio picked up a signal so extraordinary that the astronomer who discovered it scribbled, "Wow," in red ink on the printout, a name that would echo through history. For 72 seconds, a narrowband radio burst poured in from the direction of Sagittarius, blasting at a frequency of 1420 MHz, the exact wavelength hydrogen emits in the cold depths of space. Then, just as suddenly as it began, the signal vanished. No one has ever heard it again. What makes the WOW signal so electrifying isn't just its mystery, it's how perfectly it matched what scientists predicted an extraterrestrial transmission might look like. Natural cosmic phenomena tend to produce broad, messy radio waves, but this was a razor-sharp spike, as if someone had tuned a cosmic transmitter to the universe's most basic element. The signal's intensity rose and fell exactly as you'd expect if it originated from a distant planet rotating into and out of view. Even the frequency was significant. Hydrogen is the most abundant element in the cosmos, a logical choice for any civilization trying to announce its presence. For decades, astronomers have chased explanations. Some dismissed it as a passing satellite or a rogue signal bouncing off space debris, but the WOW signal's frequency was protected by international agreement. No earthly transmitter should have been using it. Others pointed to comets, suggesting their hydrogen clouds might mimic such a burst, but none were in the right place at the time, the most unsettling possibility. That we caught a single, fleeting glimpse of an alien beacon, one that either wasn't meant for us or stopped transmitting before we could find it again. The search hasn't stopped. Modern machine learning algorithms now sift through old telescope data, hunting for overlooked patterns or faint echoes of the original signal. Meanwhile, projects like Breakthrough scan the same patch of sky with instruments thousands of times more sensitive, hoping to catch a repeat. But silence persists, leaving us with a haunting question. Was the WOW signal a cosmic one-off, a bizarre quirk of nature, or the first whisper of a conversation we weren't ready to join? Perhaps the most profound lesson of the WOW signal isn't about aliens at all, but about how we explore the unknown. It reminds us that the universe is vast enough to hide countless secrets in plain sight, and that sometimes the most tantalizing discoveries are those that refuse to be solved. One brief blip, one scribbled note, and suddenly the cosmos feels alive with possibility waiting just beyond our reach to surprise us again. Take a deep breath. What you're inhaling isn't just empty air. Even in the void of space where nothing seems to exist, there's a hidden frenzy of activity at the smallest scales. This is the quantum vacuum, a realm where empty space is anything but. According to quantum physics, every cubic centimeter of the universe buzzes with fleeting particles and antiparticles that materialize and annihilate in fractions of a second. They borrow energy from the fabric of reality itself, existing just long enough to obey the universe's accounting rules before vanishing back into the void. It's as if the cosmos is built on a foundation of invisible fireflies, flickering in and out of existence too quickly to catch, but their effects are very real. The first experimental proof of this quantum chaos came in 1948, when physicist Hendrik Casimir predicted that two metal plates placed incredibly close together in a vacuum would be pushed toward each other by the sheer pressure of these virtual particles. Think of it like this: outside the plates, an infinite variety of particle wavelengths can exist, but inside the narrow gap, only certain wavelengths fit. This imbalance creates a measurable force now called the Casimir effect, like an invisible hand nudging the plates together. When scientists finally observed this in labs decades later, it confirmed that the vacuum isn't passive. It's a dynamic, seething foam with tangible energy. Now imagine tapping into that energy. Some theorists speculate that zero-point energy, the lowest possible energy state of this quantum froth, could be the ultimate power source. Calculations suggest the vacuum energy in a single light bulb's volume could boil Earth's oceans, if only we knew how to extract it. NASA Eagleworks lab once explored the far-fetched idea of a warp drive that might manipulate quantum vacuum fluctuations to bend spacetime, though the physics remains speculative. More realistically, researchers are probing whether these fluctuations could explain dark energy, the mysterious force accelerating the universe's expansion. If the vacuum's energy density changes over time, it might be stretching the cosmos itself, but the wildest possibilities lie in propulsion. The idea of a quantum vacuum thruster suggests a spacecraft could push against these virtual particles like a sailboat catching wind without needing traditional fuel. Experiments with devices like the M drive have sparked controversy, with some claiming to measure thrust from nowhere, though most scientists attribute the results to experimental error. Still, the dream persists. What if we could engineer materials that interact with the quantum foam, turning the vacuum into an engine? The challenges are staggering, but the payoff would redefine space travel. Perhaps the most mind-bending twist is the connection to higher dimensions. Some unified theories, like string theory, propose that virtual particles are glimpses of extra-dimensional physics bleeding into our reality. If true, the quantum vacuum might be a shadow of something far grander, a hidden layer of the universe where the rules we know are just the beginning. What makes this horizon so thrilling isn't just the science, but the audacity of the questions. We're not just studying particles or forces, we're probing the fundamental nature of existence itself. Every experiment, from Casimir's plates to futuristic propulsion concepts, peels back another layer of the vacuum's secrets, and with each discovery, we edge closer to answering one of physics' deepest riddles: what really lies beneath the silence of empty space? Beyond the orbit of Neptune, where sunlight is just a faint glimmer, lies a frozen graveyard of cosmic leftovers, the Kuiper Belt. This vast donut-shaped region is home to countless icy bodies, each one a pristine relic from the solar system's infancy. Unlike the rocky asteroids closer to the Sun, these objects are time capsules, preserving materials untouched since the planets first formed 4.6 billion years ago. Among them, one peculiar world stands out: Arakoth, a contact binary that looks less like a planet and more like two pancakes glued together. When NASA New Horizons spacecraft flew past it in 2019, the images stunned scientists. Here was an object so ancient, its surface hadn't been eroded by heat or impacts. It was a fossil from the dawn of our cosmic neighborhood. Arakoth's bizarre shape isn't just a curiosity, it's a clue to how planets are born. Prevailing theory suggests that dust grains in the early solar system slowly clumped together, forming pebbles, then boulders, and eventually planetesimals, the building blocks of worlds. But Arakoth's two distinct lobes, gently fused together, suggest a different story. Instead of violent collisions, its formation might have been a slow, delicate dance, with two separate objects spiraling closer until they touched at walking speed. This, a gentle merger model, challenges traditional ideas of planetary assembly, hinting that the outer solar system was more like a cosmic ballet than a demolition derby. The surprises don't stop there. Spectroscopic analysis revealed Arakoth's surface is coated in methanol ice and complex organic molecules, the kind that could have seeded life on Earth if delivered by comets. This raises a tantalizing question. Did the Kuiper Belt's icy bodies ferry water and probiotic chemistry to our planet? Upcoming missions like the European Space Agency's Comet Interceptor aim to test this by studying volatile ices on similar objects. If confirmed, it would mean Earth's oceans and perhaps even the ingredients for life originated in this distant, frozen realm. But the Kuiper Belt's mysteries go beyond Arakoth. Some objects like Haumea spin so fast they're stretched into ellipsoids, while others have moons orbiting at bizarre angles. Then there's the so-called Kuiper Cliff, where the population of objects abruptly drops off, as if something, perhaps an unseen planet, scoured the region clean. Every discovery peels back another layer of the solar system's history, revealing a past far more dynamic and strange than we ever imagined. What makes this horizon so compelling is its duality. The Kuiper Belt is both a museum and a laboratory, a place where we can study the solar system's raw materials while testing bold new theories of how worlds form. With missions like New Horizons paving the way, we're not just exploring distant ice chunks, we're reading the opening chapters of our own origin story, written in frost and rock at the edge of the light. Far beyond the Kuiper Belt, past Pluto's lonely orbit, lies a realm so distant it defies comprehension, the Oort Cloud. Imagine a vast spherical shell of icy debris stretching nearly halfway to the nearest star, held by the sun's gravitational whisper. This cosmic frontier isn't just a collection of frozen leftovers. It's a dynamic archive of our solar system's wild youth, where trillions of objects drift in perpetual twilight. Most are no larger than mountains, but some could rival planets' hidden giants whose gravitational fingerprints we've only begun to trace. The first hints of this mysterious population came from long-period comets, those rare, blazing visitors that take thousands or even millions of years to complete a single orbit. Unlike their short-period cousins from the Kuiper Belt, these comets arrive from every direction, not just the solar system's flat plane. This spherical distribution pointed to an unseen reservoir proposed by astronomer Jan Oort in 1950. But the cloud's sheer scale makes direct observation nearly impossible. Its inner edge begins roughly 2,000 times farther from the Sun than Earth, and its outer reaches extend perhaps 100 times farther still. What truly electrifies astronomers are the gravitational anomalies suggesting something massive is stirring this icy deep, the most famous candidate. Planet 9, a hypothetical world up to 10 times Earth's mass, whose existence could explain the clustered orbits of distant Kuiper Belt objects. These small bodies share peculiar orbital tilts and elongated paths, as if sculpted by an unseen shepherd. Yet Planet 9 might not be alone. Some simulations suggest multiple undiscovered worlds could lurk in the Oort Cloud, each tugging on its neighbors in an intricate dance we're only starting to map. Then there's the biological potential locked in these frozen wanderers. When Oort Cloud comets plunge sunward, their ices vaporize, releasing organic molecules like formaldehyde and hydrogen cyanide, the raw ingredients for life. Recent studies reveal some even carry ribose, a sugar critical for RNA. This raises a staggering possibility. These drifting time capsules might have seeded Earth with life's building blocks during the solar system's violent early days. The coming decade could rewrite our understanding of this frontier. Next-generation telescopes like the Vera Rubin Observatory will scan for moving objects fainter than ever before, while missions like the Interstellar Probe aim to pierce the Oort Cloud's inner layers. What we find could upend textbooks not just about our solar system's boundaries, but about how planetary systems everywhere store and exchange the ingredients for life. The Oort Cloud isn't just a relic, it's a living library waiting for us to decode its frozen pages. In the vast, silent expanse beyond Neptune, NASA Pioneer 10 and 11 spacecraft carried humanity's first physical messages to the star's gold plaques etched with symbols of our existence. But as these trailblazing probes ventured deeper into the void, something peculiar happened. Their trajectories began deviating from predictions with a discrepancy so small you could miss it in a spreadsheet, yet large enough to rewrite physics. This was the Pioneer Anomaly, a gravitational puzzle that would haunt scientists for decades. The numbers were maddeningly precise. Both pioneers experienced an unmodeled deceleration of about 8.74 times 10 to the minus 10 meters per second squared, roughly 10 billion times weaker than Earth's gravity. It was as if the probes were driving uphill through empty space, their speed bleeding off ever so slightly. At first, engineers suspected mundane explanations: fuel leaks, thruster misfires, or instrument errors. But after years of analysis, the anomaly persisted. Even accounting for every conceivable mechanical factor, the pioneers kept slowing down more than Newton's laws allowed. Theories erupted like supernovae. Some suggested thermal radiation, heat from the spacecraft's plutonium power sources bouncing off their asymmetrical bodies, could create a tiny but measurable push. Others proposed more radical ideas, like modified Newtonian dynamics (MUND), which tweaks gravity's equations at extremely low accelerations. A handful even speculated about unknown particles in the solar system's outer halo or unseen dimensions warping spacetime. The debate reached fever pitch when similar anomalies appeared in other missions like Galileo and Ulysses, though their data was noisier. Then came the twist. In 2012, an exhaustive study accounting for heat recoil from Pioneer's radioisotope generators seemed to solve the riddle. Thermal radiation could explain most of the drift. Case closed? Not quite. The lingering discrepancies were small but stubborn, leaving room for doubt. Perhaps more critically, the anomaly's legacy transcended its resolution. It exposed how even our most trusted physical models might fray at the edges when tested in unexplored regimes. What makes the Pioneer Anomaly so enduring isn't just the mystery, it's the humility it imposed. For 30 years, this minuscule deviation forced us to confront how little we understand about gravity's subtleties in deep space. Future missions like the Dark Energy Surveyor aim to test gravity's behavior across cosmic distances with unprecedented precision, hunting for deviations that could upend Einstein's relativity. The Pioneer's faint slowdown might yet prove to be the first whisper of a deeper truth, one hidden in the quiet between the stars. This is the paradox of exploration. Sometimes, the universe's grandest revelations come not from blazing cosmic fireworks, but from the faintest anomalies, decimal points that refuse to behave. The Pioneer Anomaly reminds us that physics isn't a finished story. It's a living dialogue where every spacecraft we send carries not just instruments, but questions. And beyond Pluto's shadow, the answers might be waiting where we least expect them. Imagine dropping a book into a fire. The pages burn, the ink fades, but in theory, every word could be reconstructed from the smoke and ashes if you had perfect knowledge of the physics involved. Now take that same book and toss it into a black hole. According to Einstein's general relativity, the book is gone forever, crushed into the singularity where even information itself is erased. But here's the catch: quantum mechanics insists that information can never truly be destroyed. This is the black hole information paradox, a clash between two foundational theories of physics that has kept scientists awake for decades. Stephen Hawking first ignited the debate in the 1970s when he showed that black holes aren't completely black. they emit faint radiation, slowly evaporating over eons. At first glance, this seemed to solve the paradox. If black holes leak energy, perhaps information escapes too, encoded in the radiation like a cosmic Morse code. But Hawking later realized a flaw. The radiation he predicted would be random, carrying no trace of what fell in. It's like burning a library and claiming the heat waves preserve the book's contents, an idea that outraged quantum theorists. The stakes couldn't be higher. If information truly vanishes in black holes, it would upend quantum mechanics, forcing us to rewrite the rules governing reality itself. Enter the firewall paradox. In 2012, a team of physicists proposed a brutal solution. Maybe the event horizon, the point of no return, isn't the smooth gateway relativity describes, but a searing wall of high-energy particles that incinerates anything crossing it. This would preserve information by preventing it from ever entering the black hole, but at a cost, violating Einstein's principle that free-falling observers should notice nothing unusual at the horizon. The backlash was immediate. A firewall would mean the laws of physics aren't just different near black holes, they're catastrophically discontinuous, like hitting an invisible barrier at the edge of the universe. The search for a compromise led to even wilder ideas. Some theorists argue that information escapes via holographic principles, where three-dimensional data about what fell in is smeared across the black hole's two-dimensional surface like a cosmic DVD. Others suggest entangled particles near the horizon create a backdoor, allowing information to tunnel out while leaving the original copy inside. A cosmic sleight of hand that would clone quantum states, another heresy. The most radical proposal: black holes might be portals to baby universes, with information leaking into an entirely separate spacetime continuum. What makes this paradox so exhilarating isn't just the intellectual tug-of-war, it's the potential payoff. Cracking it could reveal how spacetime itself emerges from deeper, more fundamental building blocks. Think of the universe as a vast quantum computer, where every particle, every force, is just information processing at the smallest scales. Black holes might be the key to reading that code, showing us how the cosmic operating system really works. Experiments with lab-grown, analog, black holes using sound waves or ultra-cold atoms are already testing these ideas, while gravitational wave detectors hunt for subtle echoes in black hole collisions that might betray hidden information. The paradox forces us to confront a humbling truth. Our two most successful theories of reality, quantum mechanics and general relativity, can't both be right when it comes to black holes. Resolving this contradiction won't just tidy up astrophysics. It could unveil a new layer of existence where space and time aren't the backdrop of the universe, but something far stranger, a dynamic, emergent phenomenon woven from threads we're only beginning to grasp. Every black hole isn't just a cosmic vacuum cleaner. It's a locked safe, and inside might be the blueprint for a theory of everything. The cosmic microwave background, the faint afterglow of the Big Bang, should be the ultimate cosmic equalizer, a nearly uniform sea of radiation stretching across the entire sky. But when scientists mapped it with unprecedented precision, they stumbled upon something unsettling. The temperature fluctuations weren't random. Instead, they aligned eerily with our solar system's ecliptic plane, as if the universe had scribbled a cryptic arrow pointing directly at us. Astronomers dubbed this the axis of evil, not for any malevolence, but because it threatened one of cosmology's bedrock principles, the idea that the universe looks roughly the same in all directions, no matter where you stand. At first, researchers dismissed it as a fluke. After all, the universe is vast and statistical anomalies are inevitable. But as more data poured in from missions like WMAP and Planck, the alignment persisted. The odds of this happening by chance, less than 1 in 10,000. Suddenly, the question wasn't just about measurement errors, it was about whether we'd misunderstood the cosmos itself. Could this axis be a fossil imprint from before the Big Bang, a scar left by some primordial structure that predated our universe? Some theorists speculate it might be evidence of a collision with another bubble universe in the multiverse, leaving a gravitational bruise on our cosmic infancy. Others wonder if dark energy or undiscovered physics could be warping space-time on scales we've barely begun to probe. Then there's the unsettling alternative. What if we're seeing the universe wrong? The cosmological principle assumes no special place for Earth, but the axis of evil hints that our local patch of space might be strangely unique. It's as if we've spent centuries mapping ocean currents only to realize we've been floating in a whirlpool the whole time. Critics argue it could still be an artifact. Perhaps our instruments are subtly biased, or galactic dust distorts the measurements in ways we haven't fully accounted for. Yet, even after painstaking checks, the signal lingers, whispering that the universe might not be as indifferent to our existence as we once thought. The implications ripple outward. If the axis is real, it could mean the Big Bang wasn't the true beginning but a phase transition in a larger, older cosmos. Or perhaps space-time has a hidden grain like wood, with properties that vary along different axes. Future experiments like next-generation CMB telescopes and 3D maps of galaxy distributions aim to test these wild ideas. What's at stake isn't just one anomaly, it's the foundation of modern cosmology. The axis of evil doesn't just challenge our models, it dares us to imagine a universe far stranger, far more interconnected than we ever dreamed. And that's the thrill of it. Sometimes, the most unsettling discoveries are the ones that crack open entirely new ways of seeing everything. The moon shouldn't have a magnetic field, at least, not according to everything we know about planetary science. With a core too small and cold to churn molten metal like Earth's dynamo, our satellite should be as magnetically inert as a lump of rock. But when Apollo astronauts brought back lunar samples in the late 1960s and 70s, the evidence was undeniable. Tiny mineral grains locked in ancient lava flows were magnetized, as if frozen in the grip of a vanished magnetic field nearly as strong as Earth's today. This discovery sent shockwaves through astrophysics. How could a world barely a quarter our size, long assumed to be geologically dead, have once generated such a powerful force? One leading theory points to cosmic violence. Imagine a Mars-sized asteroid slamming into the moon in its infancy, delivering a shockwave so intense it temporarily stirred the lunar core like a spoon in a cup of coffee. Simulations show such an impact could have jump-started a short-lived dynamo, unleashing a magnetic field for a few 100 million years before fading into silence. Others argue the moon's early orbit held the key. Billions of years ago, it may have spun much closer to Earth, its core stretched and heated by tidal forces in a gravitational tug-of-war. Like kneading dough, this friction could have generated enough internal motion to power a magnetic engine, until the moon drifted away and the field sputtered out. But the wildest idea, the moon's core might not be as dormant as we think. Recent measurements from NASA, a lunar reconnaissance orbiter, detected weak magnetic anomalies swirling across the surface, hinting at pockets of residual magnetism or even fleeting electrical currents deep below. If confirmed, it would mean the moon's heart isn't entirely still, just sleeping, with embers of its ancient dynamo still flickering in the dark. The answer could rewrite planetary science. Upcoming Artemis missions aim to drill into the moon's volcanic plains, retrieving rocks that formed when the magnetic field was active. By analyzing their magnetic signatures, scientists hope to reconstruct the field's strength and direction, piecing together the moon's hidden history like a cosmic detective story. But the implications stretch far beyond our satellite. If small, rocky worlds without active dynamos can generate magnetic fields through impacts or tidal heating, then moons like Europa or distant exoplanets might harbor similar surprises, shielding potential life from deadly cosmic radiation with invisible, temporary force fields. What makes this mystery so captivating isn't just the science. It's the moon's quiet defiance of expectations. It reminds us that even the most familiar worlds can hold radical secrets, waiting for the right tools, the right missions to reveal them. Every magnetized grain in those Apollo samples is a time capsule, whispering clues about a time when the moon wasn't just a silent companion in our sky, but a dynamic world with a magnetic soul of its own. On the morning of June 30th, 1908, a fireball brighter than the sun tore across the Siberian sky near the Tunguska River. Moments later, an explosion equivalent to 10 to 15 megatons of TNT, nearly 1,000 times more powerful than the Hiroshima bomb, flattened 80 million trees across 2,000 square kilometers. Windows shattered hundreds of kilometers away, and seismic waves circled the globe twice. Yet when researchers reached the remote site decades later, they found no crater, no meteorite fragments, just a radial pattern of scorched, toppled trees pointing outward from ground zero like the spokes of a broken wheel. This cosmic whodunit has puzzled scientists for over a century. The leading theory suggests a stony asteroid or icy comet, roughly 60 meters wide, entered Earth's atmosphere at 54,000 kilometers per hour, heating the air around it to 44,000 degrees Celsius. The pressure and heat caused it to explode 5 to 10 kilometers above the surface, unleashing a shock wave that leveled the forest without ever touching down. But the absence of definitive debris keeps other explanations alive. Could it have been a chunk of antimatter from deep space, annihilating itself in a flash of gamma rays upon contact with our matter-rich atmosphere? Or perhaps a primordial black hole, no larger than an atom but as massive as a mountain, passed through Earth like a bullet through tissue, leaving no trace except the devastation in its wake? Tunguska isn't an isolated event. Historical records describe similar airbursts, like the mysterious explosion over the Mediterranean in the year 584 that set the sky on fire, or the 1930 Kuiper event in Brazil where hundreds of kilos of extraterrestrial material rained down without warning. Modern monitoring reveals these happen more often than we thought. In 2013, a 20-meter-wide meteor exploded over Chelyabinsk, Russia, with 30 times the energy of the Hiroshima bomb, injuring over 1,500 people. Unlike Tunguska, this one was caught on dashboard cameras, a stark reminder that our planet is constantly bombarded by objects we rarely see coming. What makes these airbursts so dangerous isn't just their power, but their stealth. Traditional asteroid detection relies on spotting sunlight reflecting off approaching rocks, but small, dark, or icy bodies can slip through until it's too late. A Tunguska-sized event over a major city could kill millions, yet we've catalogued less than 40% of near-Earth objects in this size range. The solution? Next-generation telescopes like the Vera Rubin Observatory, which will scan the entire visible sky every few nights, coupled with space-based infrared sensors to spot cold, fast-moving threats. The Tunguska event wasn't just a fluke, it was a warning. Every few centuries, Earth crosses paths with something capable of unleashing continental-scale destruction without leaving a crater. Whether it's a comet fragment, a rogue antimatter pebble, or something even stranger, one thing's certain: the next Tunguska is out there, ticking toward an inevitable encounter. The question isn't if, but when, and whether we'll be ready to meet it with more than just curiosity. 4 billion years ago, our sun was a faint, cooler ember 30% dimmer than it is today. By all rights, Earth should have been a frozen wasteland, locked in ice from pole to pole. Yet geological evidence paints a different picture. Ancient rocks show clear signs of liquid water, even rivers and oceans during this so-called faint young sun era. This glaring contradiction isn't just a curiosity, it's a window into how planets defy expectations to create habitable conditions. One leading theory points to Earth's early atmosphere as the hero of this story. Unlike today's nitrogen and oxygen-rich air, our planet likely had a dense cloak of carbon dioxide and methane greenhouse gases that trapped heat like a cosmic blanket. Methane, in particular, packs a punch, molecule for molecule. It's over 25 times more effective at warming than CO2. Some models suggest methane concentrations could have been 10,000 times higher than modern levels, turning Earth into a planetary sauna despite the weak sunlight. But where did all this methane come from? The answer might lie in microscopic life. Primitive microbes called methanogens, thriving in oxygen-free environments, could have produced vast quantities of the gas, creating a feedback loop where life itself sustained the conditions for its survival. Another piece of the puzzle involves Earth's albedo, how much sunlight it reflected back into space. With fewer clouds and darker, rock-dominated landscapes, the young planet may have absorbed more solar energy than we'd expect. Some simulations even suggest that a faster spinning Earth, with days lasting just 6 hours, could have distributed heat more efficiently across the globe, preventing ice from gaining a foothold. The implications for exoplanet hunting are profound. If Earth could stay warm under a faint sun, then red dwarfs, dim, long-lived stars previously dismissed as too cold for habitability, might host life-friendly worlds after all. Telescopes like James Webb are now searching for methane-rich atmospheres around these stars, testing whether the faint young sun paradox is a quirk of our solar system or a universal strategy for life. But the most tantalizing question isn't just how Earth stayed warm, it's how close we came to freezing. Geological records hint at periods of extreme glaciation, suggesting our planet teetered between greenhouse and icehouse states. This delicate balance forces us to confront a humbling truth. Habitability isn't guaranteed. It's a fragile dance between atmosphere, geology, and biology, one that could easily have tipped the other way. Solving this paradox isn't just about rewriting Earth's history. It's about recognizing how rare or how common our pale blue dot might truly be in the cosmos. At the very edge of our solar system, where the sun's influence wanes and interstellar space begins, a Voyager probe stumbled upon something no one predicted, a cosmic barrier so dense with high-energy particles, it's as if the galaxy itself erected an invisible fence. This unexpected wall isn't made of matter as we know it, but a turbulent soup of charged particles piled up like waves crashing against a shore. Scientists call it the Galactic Barrier, and its discovery has forced us to rethink everything we thought we knew about the boundary between our solar bubble and the vast ocean of the Milky Way. The first hints emerged when Voyager 1, humanity's farthest-flung spacecraft, crossed the heliopause in 2012, the point where the solar wind, a stream of charged particles from the sun, finally surrenders to the pressure of interstellar space. But instead of a smooth transition, Voyager encountered a chaotic zone where particle densities spiked tenfold. Imagine sailing toward the open sea, only to find a churning whirlpool at the river's mouth. Voyager 2 confirmed the phenomenon years later, proving this wasn't a fluke but a fundamental feature of our solar system's frontier. What's causing this particle pileup? One theory points to the sun's magnetic field, which stretches far beyond Pluto like an invisible leash. As the solar system moves through the galaxy, this magnetic bubble, the heliosphere collides with interstellar winds, compressing particles at its edge like snow piling against a plow. But there's a twist. The barrier's intensity suggests something bigger is at play. Galactic magnetic fields woven through the Milky Way like invisible threads might be amplifying this effect, creating a shock zone where stellar and interstellar forces clash. The implications are staggering. If the barrier is shaped by larger galactic structures, it could mean our heliosphere isn't a perfect bubble but a distorted, comet-like shape, sculpted by forces we've barely begun to map. Future missions like NASA's Interstellar Probe, slated to launch in the 2030s, aim to chart this no-man's land in 3D, revealing whether other star systems have similar barriers or if ours is a cosmic oddity. What makes this discovery so thrilling isn't just the science, it's the metaphor. The Galactic Barrier is a reminder that even in the emptiness of space, there are borders we don't yet understand, places where the universe refuses to behave as our models predict. Every particle detected by Voyager is a message in a bottle, tossed back from the edge of the known, urging us to look deeper. And as we do, we're not just exploring space, we're learning how to read the invisible lines the galaxy has drawn around us. Some stars flicker like distant candles in the cosmic dark, but none behave quite like KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this unassuming yellow dwarf should be as stable as our own sun. Instead, it's become astronomy's greatest wild card, dimming unpredictably by up to 22%, a staggering drop that defies all conventional explanations. When astronomer Tabetha Boyajian first spotted these bizarre fluctuations in 2015, the data looked less like a natural phenomenon and more like something out of science fiction. Initial theories ranged from the mundane to the extraordinary. Could a swarm of comets, thousands of times more dense than anything in our solar system, be eclipsing the star? Or was this the signature of an alien megastructure, a Dyson swarm of energy-harvesting panels built by an advanced civilization? The latter idea, though sensational, wasn't entirely baseless. Natural objects typically block starlight in symmetrical, predictable patterns, but Tabby's star dimmed erratically with no discernible rhythm. For a brief moment, it seemed humanity might have stumbled upon the first evidence of intelligent life beyond Earth. Then came the dust. Spectroscopic analysis revealed fine particulate matter swirling around the star, scattering light in ways that could account for some of the dimming. But here's the catch: while dust explains the short-term dips, it doesn't solve the bigger mystery. Over the past century, Tabby's star has faded by nearly 20% overall, a slow, steady decline that no known dust cloud could cause. This long-term dimming points to something far more profound, perhaps a catastrophic cosmic event unfolding in slow motion. One compelling theory suggests Tabby's star recently devoured a planet, leaving behind a dissipating debris field that now intermittently blocks its light. Picture a gas giant spiraling too close, torn apart by gravitational forces, its remains forming an irregular veil of vaporized rock and metal. Alternatively, the star might be surrounded by a massive, warped ring system like Saturn's rings, scaled up to stellar proportions, casting complex shadows as they rotate. There's even speculation about a captured rogue planet, its icy mantle evaporating into a transient atmosphere that periodically obscures the star. What makes Tabby's star so captivating isn't just the unanswered questions. It's the way it forces us to rethink the boundaries of natural phenomena. With every new observation, astronomers are uncovering cosmic processes we never imagined possible. The star's behavior challenges our assumptions about stellar evolution, planetary formation, and even the limits of observational science. Future telescopes equipped with high-resolution spectrographs and next-generation optics may finally unravel this enigma, revealing whether it's a freak celestial accident or a signpost to discoveries we've yet to dream up. In the end, Tabby's star is more than an anomaly. It's a masterclass in cosmic humility. It reminds us that the universe doesn't owe us tidy explanations, and that the most extraordinary revelations often begin with a single, inconvenient data point that refuses to fit. Whether the answer lies in shattered planets, alien engineering, or something entirely unforeseen, one thing's certain: this star will keep us guessing, and that's what makes it unforgettable. Imagine measuring the length of a room with two different rulers. Each one gives you a slightly different answer, and neither is wrong. That's the essence of the Hubble Tension, one of modern cosmology's most perplexing puzzles. Depending on whether we study nearby stars or the faint glow of the early universe, the rate of cosmic expansion, the Hubble constant disagrees by nearly 10%. It's as if the universe itself is giving us mixed signals, and the implications could rewrite everything we thought we knew about space, time, and the forces shaping reality. The roots of this mystery stretch back to the 1920s, when Edwin Hubble first noticed galaxies racing away from us, their light stretched into redder wavelengths by the expanding fabric of space. Today, we measure this expansion in two primary ways. The first method, called the distance ladder, uses pulsating stars called Cepheids and explosive supernovae in nearby galaxies as cosmic yardsticks. These observations suggest the universe is expanding at about 73 kilometers per second per megaparsec. But when we turn to the cosmic microwave background, the afterglow of the Big Bang, the rate drops to 67. That gap might seem small, but in the precise world of cosmology, it's a chasm. So where does this discrepancy come from? One tantalizing possibility is that our universe isn't just expanding, it's evolving. Dark energy, the mysterious force accelerating cosmic expansion, might not be constant as we've assumed. Instead, it could be growing stronger over time or interacting with dark matter in ways we haven't accounted for. Some theorists speculate about dark radiation, an exotic form of energy from the early universe that subtly altered the rate of expansion in ways we're only now detecting. Others wonder if the fabric of spacetime has hidden wrinkles, large-scale inhomogeneities that distort our measurements like funhouse mirrors. The James Webb Space Telescope is now zeroing in on this puzzle with unprecedented precision. By observing Cepheids and supernovae in infrared light, piercing through cosmic dust that Hubble couldn't, it may finally reconcile these conflicting numbers. But the tension has already taught us something profound. Our standard model of cosmology, while staggeringly successful, is incomplete. Like a map missing entire continents, it guides us beautifully through known territory, but falters at the edges of understanding. What makes this horizon so electrifying isn't just the scientific challenge, it's the reminder that the universe refuses to be pinned down. Every discrepancy, every unexplained decimal point, is an invitation to look deeper. Whether the answer lies in new physics, revised methods, or something beyond our current imagination, one thing's certain: the Hubble tension isn't just a problem to solve. It's a doorway to discoveries we haven't even dreamed of yet. Venus has always been the solar system's paradox, a planet so similar to Earth in size and composition, yet transformed into a scorching, acidic hellscape by a runaway greenhouse effect. So when astronomers announced in 2020 the detection of phosphine gas in its upper clouds, the scientific world erupted. On Earth, this foul-smelling molecule is almost exclusively produced by microbes thriving in oxygen-free environments like swamps and animal guts. Finding it floating 50 kilometers above Venus's surface, where temperatures and pressures are eerily Earth-like, raised an electrifying question: could there be life clinging to the skies of our closest planetary neighbor? The discovery wasn't made lightly. researchers spent years analyzing data from the James Clerk Maxwell Telescope in Hawaii and the ALMA array in Chile, ruling out known geological or chemical processes that might explain the signal. Volcanic activity, lightning, even meteorite impacts, none could account for the concentrations observed. Phosphine shouldn't last long in Venus's sulfuric acid-laden atmosphere. Something had to be replenishing it. The most tantalizing possibility, aerial microorganisms drifting in cloud droplets where water, sunlight, and trace nutrients might sustain them. It's not as far-fetched as it sounds. On Earth, bacteria have been found thriving in similarly hostile environments, from acidic hot springs to the upper atmosphere. But science thrives on skepticism, and the phosphine debate quickly turned contentious. Some teams failed to reproduce the detection, attributing the original signal to data processing errors or sulfur dioxide interference. Others proposed exotic abiotic origins, like unknown chemical reactions between Venus's surface minerals and its corrosive atmosphere. The truth is, we know staggeringly little about Venus's geochemistry. Its crushing surface pressure 92 times Earth's, and lead melting temperatures make exploration brutally difficult. Past landers like the Soviet Venera probes lasted mere minutes before succumbing to the inferno, leaving vast gaps in our understanding of how the planet's atmosphere interacts with its geology. That's why upcoming missions like NASA Da Vinci Plus and ESA's Envision are so critical. Da Vinci will plunge through Venus's clouds, sniffing for phosphine and other potential biosignatures while mapping atmospheric composition layer by layer. Envision, equipped with advanced spectrometers, will scan for surface mineralogy that might feed atmospheric chemistry. Together, they could finally answer whether phosphine is a fingerprint of life or the product of previously unseen planetary processes. What makes this mystery so compelling isn't just the hunt for aliens, it's the reminder of how narrow our definition of habitability might be. If life can persist in Venus's acidic clouds, it forces us to reconsider every assumption about where biology might take root, from the methane seas of Titan to the subsurface oceans of Europa. The phosphine puzzle isn't merely about one molecule. It's a challenge to expand our imagination of what life can be and where it might hide, even in our own cosmic backyard. Mars should be a silent world when it comes to methane, or so we thought. This simple gas, made of just one carbon atom and 4 hydrogen atoms, is a scientific beacon on the red planet. On Earth, 95% of methane comes from living organisms, from burping cows to microbes in wetlands. So when NASA Curiosity rover began sniffing out sporadic methane spikes in Gale Crater, some 10 times above background levels, it sparked a detective story with 2 possible endings, geology or biology. But here's the twist that deepens the mystery. While Curiosity catches these fleeting whiffs at ground level, orbiters like ESA's Trace Gas Orbiter scan the entire planet and seed almost nothing. It's as if Mars is playing a cosmic game of hide and seek with us, revealing its secrets only in brief, localized whispers. The rover's most tantalizing detection came in 2019, when methane levels suddenly surged to 21 parts per billion, the highest ever recorded. Then, within days, the signal vanished. This erratic behavior points to an active, possibly underground source. One theory suggests methanogenic microbes could be thriving in briny aquifers beneath the surface, metabolizing hydrogen and carbon dioxide to produce the gas. If true, it would mean life found a way to persist in Mars's harsh subsurface, much like extremophiles in Earth's deepest caves or hydrothermal vents. But there's a geological counterargument. Certain mineral reactions, like serpentinization, can also produce methane when water interacts with olivine-rich rocks. Without drilling deeper than Curiosity's 7-centimeter scoop can reach, we're left guessing. The orbital discrepancy adds another layer of intrigue. Why don't spacecraft see the methane that Curiosity does? One possibility is timing. The gas might be destroyed faster than expected by ultraviolet radiation or chemical reactions with Martian dust, leaving only brief, localized plumes for surface instruments to catch. Alternatively, the methane could be trapped beneath surface crusts, escaping only through cracks or during warmer seasons when subsurface ice thins. Some researchers even speculate about a cold sink effect, where methane clings to soil particles at night, invisible to orbiters but detectable by rovers as temperatures rise. Solving this puzzle will take more than remote observations. Future missions like NASA's Mars Life Explorer aim to drill 2 meters down, where any organic molecules or even living microbes could be shielded from surface radiation. Meanwhile, the ExoMars Rosalind Franklin rover, equipped with a 6-foot drill, could finally reach the depths where answers lie. Until then, every methane spike is a breadcrumb on a trail that might lead to one of humanity's greatest discoveries, or remind us just how cleverly a lifeless planet can mimic the signs of biology. What makes this mystery so captivating isn't just the hunt for Martians. It's the way Mars forces us to question our assumptions. Every time we think we understand its rhythms, the planet throws us a curveball, proving that even our closest planetary neighbor still holds secrets in its rusty soil. Whether the methane comes from microbes, minerals, or some process we haven't yet imagined, one thing's certain: Mars is far from dead. It's a world that breathes, and we're just beginning to hear its whisper. We think of galaxies as islands of light adrift in a vast cosmic ocean, but the truth is far stranger. Those glittering cities of stars are connected by an invisible network, a web of superheated gas so diffuse it's near impossible to detect. This is the missing baryon problem in action. Calculations show there should be twice as much normal matter in the universe as we've found in stars and galaxies combined. The rest, it's hiding in plain sight, woven between galaxies in filaments of ionized gas hotter than 1,000,000 degrees, stretching millions of light years across the void. Detecting these ghostly threads is like trying to photograph a spider's web draped across a foggy night sky. The gas is so thin, just 1 atom per cubic meter, that it barely interacts with light. But when galaxies move through it, they leave behind wakes of compressed plasma, like ships churning up ocean foam. Astronomers first caught glimpses of this structure in the 2000s, using distant quasars as cosmic flashlights. As their light passes through the web, certain wavelengths get absorbed, revealing the fingerprint of ionized oxygen and other elements. These absorption lines are the smoking gun proof that what looks like empty space is actually a dynamic highway of matter, cycling between galaxies and the intergalactic medium over billions of years. The real breakthrough came with X-ray telescopes like Chandra and Exomoons, which spotted the gas's faint glow where it's densest around galaxy clusters. But to map the web's full extent, we'll need next-generation tools like ESA's Athena mission, launching in the 2030s. With resolution 100 times sharper than current X-ray observatories, Athena will hunt for the telltale emission of oxygen ions tracing these filaments, reconstructing the web in 3D for the first time. What makes this so revolutionary isn't just filling the baryon budget, it's seeing the universe's hidden architecture. These filaments aren't passive backdrops, they're the scaffolding upon which galaxies grow, funneling gas into star-forming regions and regulating cosmic evolution like an invisible hand. Here's the twist: this gas isn't just dark, it's ancient. Simulations suggest half of it may predate the first stars, pristine material untouched by supernova or black holes. Studying its composition could reveal the universe's original elemental recipe preserved in these cosmic ice veins. Some filaments might even be dark galaxies, failed structures that never ignited stars, their gas too diffused to collapse. Others could be intergalactic recycling plants, where material ejected by galactic winds gets mixed and redistributed across epochs. The cosmic web reminds us that emptiness is an illusion. Between every galaxy, every star, space thrums with invisible activity, a living network where most of the universe's ordinary matter has been hiding all along. Unlocking its secrets won't just solve our accounting problem. It will show us how the universe builds its greatest structures from threads we're only beginning to see. There's a ghost in the particle Zoo-1 so elusive, it can pass through a light year of lead without a single collision. Neutrinos, the universe's most aloof particles, are born in the hearts of stars, the fury of supernovae, and even the decay of atoms in a banana. For decades, physicists assumed these phantoms were massless, racing through the cosmos at the speed of light without a care. Then, in the late 1990s, experiments in Japan and Canada caught them in the act of identity theft. Neutrinos were oscillating, changing flavors between electron, muon, and tau types mid-flight, a sleight of hand only possible if they had mass. This discovery upended the standard model of particle physics, revealing a cosmic mystery. Why are neutrinos astronomically lighter than any other particle we know? The numbers defy intuition. An electron, the next lightest particle, outweighs the heaviest neutrino by at least 4 million times. It's like comparing a feather to a battleship. One leading theory, called the seesaw mechanism, suggests neutrinos have ultra-heavy siblings we've yet to detect. Particles so massive, their existence would pull neutrino masses down to the tiny values we observe. Imagine a playground seesaw. If one side carries an invisible elephant, the other side, the neutrinos we know, would be lifted into extreme lightness. Some versions of this idea require extra spatial dimensions, where these heavy neutrinos could hide, their gravity leaking into our 3D world like whispers through a wall. But the real stakes go beyond particle physics. Neutrinos might hold the answer to one of existence's biggest riddles. Why is the universe made of matter at all? According to the Big Bang, equal amounts of matter and antimatter should have annihilated each other, leaving behind a sea of lifeless radiation. Yet here we are. Neutrinos, with their ability to oscillate between matter and antimatter states, could have tipped the scales. Experiments like Japan's T2K and the Deep Underground Neutrino experiment in the U.S. are hunting for differences in how neutrinos and antineutrinos oscillate, a smoking gun for matter's cosmic survival. The hunt for neutrino mass isn't confined to underground labs. At the South Pole, the ice cube detector transforms a cubic kilometer of glacial ice into a neutrino telescope. When a high-energy cosmic neutrino collides with an atom, it creates a flash of blue-light Cherenkov radiation that sensors buried deep in the ice can trace back to distant astrophysical cataclysms like colliding black holes or gamma-ray bursts. These messengers from across the universe carry clues about neutrino properties at energies no earthly collider can reach. What makes these ghostly particles so captivating isn't just their stealth, it's their refusal to fit neatly into our theories. Every time we think we've pinned them down, they reveal another layer of mystery. Whether the answer lies in unseen dimensions, undiscovered particles, or physics beyond the standard model, one thing's certain: neutrinos are more than cosmic specters. They're the key to understanding why the universe looks the way it does, and why we're here to ponder it at all. For over a century, Cepheid variable stars have been astronomy's most reliable mile markers, lighthouses guiding us across the cosmic ocean. These pulsating giants rhythmically brighten and dim in precise cycles, their intrinsic luminosity locked in a mathematical dance with their pulse rates. Measure the period and you know the star's true brightness. Compare that to its apparent glow from Earth and you've got its distance. It's a celestial ruler so trusted. Edwin Hubble used Cepheids to prove galaxies exist beyond the Milky Way and to uncover the expanding universe itself. But now, cracks are appearing in this golden standard, and the implications could shake the foundation of modern cosmology. The trouble began when the Hubble Space Telescope and Gaia Satellite, two of our most precise cosmic cartographers, started measuring Cepheids in the same galaxies but getting subtly different distances. At first, scientists dismissed it as measurement noise. Then came the shocker. Cepheids in young, metal-rich stellar neighborhoods pulse differently than their older, metal-poor counterparts, their brightness period relationships skewed by composition. It's as if two identical-looking stopwatches kept time at different rates depending on where they were made. This isn't just academic nitpicking. If Cepheids aren't uniform, every cosmic distance measured with them, and by extension, calculations of the universe's expansion rate and age, carries a hidden error bar. One explanation points to stellar atmospheres. Metal-rich Cepheids might have more opaque outer layers, altering how light escapes and making them appear dimmer than expected for their pulsation periods. Others suggest convection. The roiling motion of plasma beneath a star's surface plays a bigger role than models assumed, especially in younger stars with more vigorous energy transport. The most tantalizing possibility, that Cepheids themselves evolve over time, their internal structures changing as they age, rewriting the very rules we've used to decode them. The stakes couldn't be higher. Cepheids anchor the cosmic distance ladder, the step-by-step method we use to measure everything from nearby galaxies to the edge of the observable universe. If their calibration is off, it could exacerbate the Hubble tension, the troubling discrepancy in the universe's expansion rate, or even force us to reconsider the timeline of cosmic events like the formation of the first galaxies. JWST is now scrutinizing Cepheids in infrared light, piercing through dust that might have biased past measurements, while advanced 3D stellar simulations attempt to model their hidden complexities. What makes this controversy so electrifying isn't just the technical challenge, it's the philosophical reckoning. Science progresses by questioning its most trusted tools, and Cepheids remind us that even the universe's most steadfast beacons flicker with untold stories. Every pulse of light carries not just distance but history, the chemical legacy of their birthplaces, the turbulence of their interiors, and perhaps clues to physics we've yet to imagine. Solving this puzzle won't just fix our cosmic maps, it might reveal new chapters in the life stories of stars themselves. The surface of the Sun simmers at around 5,500 degrees Celsius, hot enough to vaporize any known material. Yet just above it, in the wispy outer atmosphere called the corona, temperatures soar to millions of degrees, as if you stepped away from a campfire and suddenly found yourself inside a blast furnace. This cosmic contradiction defies everything we know about heat transfer. Normally, temperatures drop as you move away from a heat source, not spike to unimaginable extremes. Solving this mystery isn't just about understanding our nearest star. It's about decoding a universal process that shapes planets, stars, and even galaxies. For decades, the leading theory pointed to the Sun's tangled magnetic fields. Imagine thousands of rubber bands stretched, twisted, and snapped by the Sun's rotation, storing immense energy. When these fields suddenly reconfigure, a process called magnetic reconnection, they release explosions akin to millions of atomic bombs. These nanoflares, too small to see individually but collectively omnipresent, could theoretically heat the corona like countless microscopic light bulbs. But when NASA Parker Solar Probe began its daring dives through the corona, it found something unexpected, a chaotic symphony of plasma waves rippling through the solar wind. These aren't gentle ripples, they're tsunamis of charged particles, accelerating and colliding with enough force to transfer energy directly into the corona's thin gas. The key might lie in a phenomenon called ion cyclotron waves. As magnetic field lines vibrate, they whip charged particles into frenzied spirals, much like a surfer catching an endless wave. Each rotation pumps energy into the particles, heating them to extreme temperatures. Parker's instruments have detected these waves resonating at frequencies that match the motions of coronal ions, offering the first direct evidence of this process in action. What's startling is how efficient it is, like a cosmic microwave oven tuned precisely to the particle's natural frequency, transferring energy with minimal waste. But the plot thickens farther from the sun's surface. Parker's data reveals turbulent swirls in the solar wind, where magnetic energy dissipates not in explosive reconnection, but through a cascade of ever smaller eddies, a process eerily similar to how energy dissipates in Earth's oceans. This suggests the corona's heat might arise from multiple mechanisms working in concert: explosive nanoflares near the surface, resonant waves at mid-altitudes, and turbulent dissipation farther out. It's not one solution but a layered puzzle, each piece dominant under different conditions. The stakes transcend astrophysics. Solar storms unleashed by coronal disturbances can fry satellites, knock out power grids, and expose astronauts to deadly radiation. If we can predict these eruptions by decoding the corona's heating mechanisms, we might finally shield our technology from the sun's worst tantrums. Beyond our solar system, the same principles could explain why black hole accretion disks glow fiercely, or why galaxy clusters are embedded in halos of ultra-hot gas. The corona isn't just a solar phenomenon, it's a cosmic laboratory, showing us how magnetic energy transforms into heat across the universe. What makes this mystery so compelling is its defiance of intuition. The corona teaches us that nature often hides its most profound truths in plain sight, in the delicate interplay of forces we're only beginning to measure. With every orbit, Parker Solar Probe peels back another layer, revealing not just how our sun works, but how magnetism shapes the universe itself, one searing particle at a time. At the heart of our galaxy, where stars crowd together in their billions and a supermassive black hole lurks in the darkness, astronomers have detected something that shouldn't be there: an eerie excess of gamma rays pulsing from the Milky Way's core. This mysterious glow, dubbed the galactic center excess, defies all conventional explanations. The energy signature matches what physicists would expect if dark matter particles were colliding and annihilating each other in the dense gravitational well of the galactic center. But there's a catch. It could also be coming from thousands of undiscovered pulsars, their spinning beams of radiation blending into a diffuse fog that tricks our telescopes. The first hints of this anomaly emerged from NASA's Fermi Gamma Ray Space Telescope, which has been mapping high-energy light since 2008. When researchers subtracted all known gamma ray sources, everything from cosmic rays colliding with gas clouds to distant quasars, they were left with an unexpected surplus radiating from within about 5,000 light-years of Sagittarius, a star, our galaxy's central black hole. The signal peaks at energies around 2 to 3 gigaelectronvolts, precisely the range predicted for certain dark matter candidates, particularly weakly interacting massive particles, or WIMP. If these hypothetical particles are real, their mutual annihilation would produce gamma rays along with other byproducts, painting a target on the galactic center where dark matter should be densest. But skeptics point to a cosmic camouflage. The Milky Way's core is a stellar graveyard teeming with neutron stars, ultra-dense remnants of dead suns that spin hundreds of times per second, shooting lighthouse-like beams of radiation. Some, called millisecond pulsars, are so old and faint they evade detection as individual objects. A population of these hidden spinners could collectively mimic the smooth gamma-ray excess we observe. Supporting this, recent analyses using machine learning have teased out faint point sources within the glow, though the debate rages over whether these are genuine pulsars or statistical noise. The answer might lie in the light's distribution. Dark matter annihilation should produce a smoothly symmetric glow, fading predictably from the center outward. Pulsars, being discrete objects, would create a clumpier signal. Current data leans slightly toward smoothness, but not conclusively. Upcoming instruments like the Cherenkov Telescope Array, with its unprecedented angular resolution, will scrutinize this region at even higher energies, hunting for the telltale flicker of individual pulsars or the unmistakable smoothness of dark matter's fingerprint. What makes this enigma so electrifying is its duality. If it's dark matter, we're glimpsing the first indirect evidence of particles that make up 85% of the universe's mass. If it's pulsars, we've underestimated how many stellar corpses hide in the galactic basement. Either outcome reshapes our understanding of cosmic landscapes, revealing either invisible matter's hidden interactions or the crowded afterlife of stars we thought we knew. The galactic center excess isn't just a puzzle. It's a crossroads where particle physics meets astrophysics, and the path we choose could lead to revolutions in both. Stretched across the cosmic map like an invisible continent, the Eridanus Supervoid isn't just empty space, it's a staggering absence, a cosmic hole so vast it could swallow thousands of galaxies whole. This billion-light-year-wide region lurking in the constellation Eridanus reveals itself not through what it contains, but through what's missing. A conspicuous cold spot in the cosmic microwave background, the afterglow of the Big Bang. Temperatures here dip slightly but significantly below the average, as if the void itself has sucked away energy from the primordial light passing through. The scale of this anomaly defies easy explanation. How could a structure this large, this empty, exist in a universe where matter is supposedly distributed like a finely woven web? One possibility takes us back to the universe's infancy. During inflation, the explosive expansion that occurred fractions of a second after the Big Bang quantum fluctuations might have left behind overdensities and underdensities in spacetime itself. The Eridanus Supervoid could be one such fluctuation, a bubble of lower density space frozen into the cosmic fabric before the first stars even ignited. If true, it would be a fossil from the most violent epoch of creation, a relic so enormous it makes galaxy clusters look like specks of dust. But there's a problem. Simulations of cosmic structure struggle to produce voids this size without violating our best models of how matter clumps together over time. That's where the wilder theories emerge. Some cosmologists speculate the supervoid might be a cosmic bruise, a dent in our universe left by a collision with another bubble universe in the multiverse. Picture two soap bubbles gently pressing together. Where they meet, space-time could be stretched thin, creating a region of diminished energy density. Others suggest it's evidence of a topological defect, a crack in space-time's structure left over from a phase transition in the early universe, like ice forming fractures as it freezes. These ideas tread the edge of science fiction, but they're rooted in legitimate, if speculative, physics. Yet not everyone is convinced the void is real. Skeptics argue the cold spot could be a statistical fluke, a cosmic mirage caused by the uneven distribution of galaxy clusters between us and the CMB. Others propose that intervening dust or foreground emissions might be distorting our measurements. The debate hinges on precision. Future CMB experiments with higher resolution, like the Simons Observatory, aim to map the cold spot's edges in exquisite detail, searching for telltale patterns that could distinguish a true underdensity from an illusion. What makes the Eridanus Supervoid so captivating isn't just its size. It's the way it forces us to question the universe's architecture. If confirmed, it would dwarf even the Hercules Corona Borealis Great Wall, currently the largest known structure, and challenge our understanding of how gravity sculpts the cosmos on the grandest scales. Whether it's a quantum fossil, a multiverse scar, or something even stranger, this cosmic blank spot reminds us that the universe reserves its greatest surprises for the places we least expect, not in the blazing galaxies or swirling nebulae, but in the silent, empty spaces between them. Most galaxies follow predictable pattern spirals with sweeping arms, ellipticals like glowing cotton balls, or messy irregulars tangled in cosmic collisions. Then there's Hoag's object, a celestial oddity so perfect it looks almost artificial. Named after astronomer Arthur Hoag, who discovered it in 1950, this ring galaxy floats in the constellation Serpens like a cosmic bullseye, its brilliant blue circle of young stars framing a golden core of ancient suns. The strangest part, the gap between the core and the ring is nearly pristine, a dark void where almost no stars reside. It's as if someone took a conventional galaxy, scooped out its middle, and left only the edges glowing, a structure so rare fewer than 1 in 10,000 galaxies resembles it. How does such a flawless ring form without the usual scars of collision? The leading theory involves a galactic hit and run. Picture a smaller galaxy, perhaps a tenth the size of Hoag's object, plunging dead center through a larger disk galaxy billions of years ago. The intruder's gravity would compress gas and dust in the disk like ripples in a pond, triggering a wave of star formation that propagated outward, leaving the core untouched. Computer simulations show this bullseye collision can indeed create ring structures, but the symmetry of Hoag's object pushes the limits of probability. The impact would need to be perfectly aligned, like threading a needle through the exact center of a spinning vinyl, record a cosmic fluke of precision. Yet there's an alternative explanation that doesn't require a collision at all. Some models suggest that resonant gravitational instabilities, natural oscillations in a galaxy's disk, could funnel gas into a ring without any outside interference. Imagine shaking a bowl of water until the liquid climbs the sides, leaving the center dry. If dense regions of a galaxy's disk tug on each other in just the right rhythm, they might sculpt gas into a perfect circle, birthing new stars along the crest of the wave. This process could explain why a handful of other ring galaxies, like the Cartwheel Galaxy, show similar structures despite no visible collision partners nearby. The mystery deepens when we peer into Hoag's object's core. Spectroscopic analysis reveals its central region is packed with stars nearly twice as old as those in the ring, a clue that the core might be a relic from an earlier epoch, while the ring represents a second act of star formation. Even stranger, Hubble images revealed another, fainter ring galaxy lurking in the distant background, visible through Hoag's object's transparent gap. This alignment is pure chance, but it's a poetic reminder that cosmic oddities might be more common than we think, hidden in plain sight until our telescopes catch them at the right angle. What makes Hoag's object so captivating isn't just its beauty, it's the way it defies categorization. Most galactic evolution follows predictable scripts, mergers, bursts of star formation, slow fading. But here, nature seems to have taken a detour, crafting something that feels almost deliberate in its perfection. Whether it's a relic of ancient violence or a self-made masterpiece, this celestial enigma reminds us that the universe reserves its most stunning surprises for those willing to look beyond the expected. Every outlier like Hoag's object isn't just a curiosity, it's a key to unlocking the untold stories of how galaxies bend, break, and sometimes, against all odds, dance alone. Galaxies don't drift randomly through the cosmos, they flow like leaves caught in a river's current. But in 2008, astronomers tracking hundreds of galaxy clusters noticed something unsettling. These colossal structures, each containing thousands of galaxies, weren't just moving, they were all streaming toward the same patch of sky near the constellations Centaurus and Hydra, as if pulled by an invisible hand. This coordinated motion, dubbed the dark flow, defies everything we know about cosmic expansion. The universe should be stretching uniformly in all directions, yet here was evidence of a mysterious asymmetry, a gravitational tug so powerful it seemed to originate beyond the edge of the observable universe. The numbers are staggering. These galaxy clusters race at speeds up to 1,000 kilometers per second, far faster than local gravitational forces can explain. Even accounting for known superclusters like the Shapley Attractor, the scale of this motion suggests an influence from something truly incomprehensible, a structure so massive it lies outside our cosmic horizon, forever hidden by the finite speed of light. One radical explanation: our universe might bear the gravitational scars of a pre-Big Bang realm. Just as ripples in a pond reveal where a stone was tossed, the dark flow could be an imprint from a neighboring spacetime bubble in the multiverse, its gravity leaking into our own like a shadow from another dimension. Critics argue the data might be an artifact, perhaps systematic errors in measuring galaxy distances or the cosmic microwave background reference frame. But the signal has persisted across multiple studies, including analyses by NASA, a Wilkinson microwave anisotropy probe, and Planck satellite. The most compelling counterpoint comes from large-scale structure surveys, which show no obvious concentration of matter in the flow's direction. If the dark flow is real, its source isn't just hidden, it's fundamentally unobservable, locked beyond the 14 billion light-year limit of our visible universe. The implications rewrite cosmology's rules. If the universe isn't isotropic, if matter and motion aren't evenly distributed, it challenges the foundational assumption that observers anywhere should see roughly the same large-scale structure. Future missions like the European Space Agency's Euclid telescope aim to test this by mapping galaxy motions in unprecedented detail, hunting for subtle deviations that could confirm or refute the flow. But the most thrilling possibility remains that we're glimpsing the gravitational echo of something primordial, a relic from before time began. The dark flow isn't just a mystery, it's a tantalizing hint that the universe's greatest secrets might lie not in what we see, but in what we can never reach. Most dying stars leave behind chaotic, swirling nebulae, turbulent clouds of gas and dust that look like abstract paintings flung across the cosmos. Then there's the Red Rectangle Nebula, a celestial anomaly so precise it seems engineered. Floating 200-300 light-years away in the constellation Monoceros, this aging star's final act defies expectation. Its outflow forms a near-perfect X-shape, framed by glowing red rungs that give it the appearance of a cosmic stop sign. This isn't random stellar graffiti, it's a masterpiece of geometric precision, and the secrets behind its symmetry could rewrite how we understand the death throes of stars like our own sun. At first glance, the red rectangle's crisp angles seem impossible. Stars typically shed their outer layers in spherical shells or erratic jets, not razor-sharp polygons. The answer likely lies in the nebula's hidden heart, not one dying star, but two. The central binary system, a red giant paired with a smaller, hotter companion, orbit so closely that their gravitational dance funnels ejected material into opposing cones. As the red giant expels gas, its partner star's gravity shears the outflow into two opposing beams, which we see edge on as an X. But there's a twist. Observations from the Hubble Space Telescope reveal ladder-like rungs between the beams, suggesting the star's orbital motion acts like a sprinkler, pulsing material outward in rhythmic bursts that stack over time like rings in a tree trunk. Yet magnetism might be the invisible sculptor. Some models suggest the red giant's magnetic field, twisted by its rotation and the companion star's influence, could channel ionized gas along rigid lines like iron filings aligning around a magnet. This would explain why the nebula's arms remain so sharply defined even as they stretch light years into space. Similar processes might occur in protoplanetary disks, where magnetic fields mold chaos into orderly spiral structures, hinting at a universal physics that favors hidden geometry amid apparent randomness. The red rectangle's significance goes beyond its beauty. It's a preview of our solar system's fate. In 5 billion years, the Sun will swell into a red giant, engulfing Mercury and Venus and possibly Earth. Whether its death produces a messy cloud or an intricate structure like the red rectangle depends on unseen factors: the Sun's rotation rate, magnetic field strength, and whether a binary companion or a surviving Jupiter stirs the pot. Already, telescopes have spotted other X-shaped nebulae, suggesting this phenomenon isn't rare, just overlooked. What makes this cosmic geometry so profound isn't just the how, but the why. Nature abhors straight lines, yet here they are a testament to the universe's hidden love for order. The red rectangle whispers that even in death, stars follow rules we're only beginning to decipher, their final breaths etched in angles and ratios as precise as any equation. As we study its rungs and rays, we're not just decoding a nebula's shape, we're reading the blueprints of stellar demise, written in a language of physics and symmetry that transcends the chaos of the cosmos. The universe isn't just expanding, it's organizing itself on scales so immense they defy intuition. Take the Hercules Corona Borealis Great Wall, a galactic filament so vast it could swallow 10,000 Milky Ways side by side and still have room to spare. Stretching over 10 billion light-years across, this behemoth isn't merely a structure, it's a cosmic continent, a web of superclusters and voids so enormous that its very existence rattles our understanding of how the universe arranges itself. According to cosmological principles, there's a theoretical upper limit to how large matter should clump together, roughly 1.2 billion light-years. Yet here's a colossus nearly 10 times that size, flaunting its defiance like a cosmic rebel. How does gravity sculpt something so monumental so soon after the Big Bang? The wall's discovery in 2013 sent shockwaves through astronomy because it wasn't just bigger, it was ancient. Its light comes from a time when the universe was barely half its current age, meaning gravity had far less time to weave matter into such an expansive tapestry. One radical explanation points to primordial quantum fluctuations, tiny ripples in spacetime during inflation, that might have seeded ultra-large density variations. Imagine blowing up a balloon with microscopic wrinkles. As it expands, those wrinkles stretch into massive folds. If certain regions of the early universe were slightly denser than others, their gravity could have drawn in surrounding matter faster, creating these colossal threads ahead of schedule. But there's a catch. Our standard models of cosmic evolution struggle to reproduce structures this size without tweaking the rules. Some theorists suggest dark energy's repulsive force might have played an unexpected role, counterintuitively helping matter cluster more tightly in specific regions by accelerating expansion elsewhere. Others speculate about exotic physics, perhaps a temporary weakening of gravity's grip in the early universe, allowing matter to clump more freely. The most mind-bending idea, that the Hercules Corona Borealis Great Wall isn't a single structure at all, but a chance alignment of multiple filaments viewed edge-on, like seeing the overlapping branches of distant trees and mistaking them for one continuous forest. The hunt for answers is driving next-generation sky surveys. Projects like the Dark Energy Spectroscopic Instrument, DAISY, are creating 3D maps of millions of galaxies, tracing the universe's large-scale structure with unprecedented resolution. What they find could reveal whether this wall is a statistical fluke or a signpost to deeper mysteries, perhaps even evidence of pre-Big Bang phenomena imprinted on the cosmos. Every new slice of the sky peels back another layer, showing us that the universe's grandest designs are still emerging from the shadows, daring us to rethink not just what's out there, but how it all fits together. Imagine a supermassive black hole, an anchor weighing millions of suns, suddenly ripped from the heart of its galaxy and hurled into the void at speeds topping 5 million miles per hour. This isn't science fiction. The Hubble Space Telescope has spotted these cosmic fugitives, quasars blazing across intergalactic space, their brilliance betraying the presence of black holes that should be nestled quietly in galactic centers. These aren't just drifting, they're fleeing, propelled by some of the most violent events in the universe. The culprit, gravitational wave recoil. When two supermassive black holes spiral toward each other in a galactic merger, their final collision doesn't just create ripples in spacetime, it can kick the merged black hole like a cosmic cannonball. Picture two spinning tops colliding. If their spins are misaligned, the energy released in gravitational waves isn't symmetrical. The imbalance launches the newborn black hole in the opposite direction, sometimes with enough force to escape its galaxy entirely. Hubble's observations of quasars offset from their host galaxy's cores provide smoking gun evidence of this phenomenon, showing these behemoths mid-flight. But where do they go? A rogue black hole's journey isn't a lonely one. As it plows through intergalactic gas, it can ignite star formation in its wake, compressing dark matter and hydrogen into glowing trails that might evolve into dwarf galaxies. These black hole contrails could explain mysterious ultra-compact dwarfs found floating near larger galaxies' stellar orphans with unusually dense cores. Even more intriguing are the invisible gravity wells left behind. A wandering black hole might not emit light, but its gravitational fingerprint could bend the paths of stars or lens distant galaxies, leaving ghostly distortions for astronomers to decode. The implications stretch beyond mere curiosity. Runaway black holes challenge our understanding of galactic evolution. If the heaviest objects can be ejected, what does that mean for the growth of galaxies? Supermassive black holes are thought to regulate star formation and shape galactic structure through feedback mechanisms. Losing one might stunt a galaxy's development or trigger chaotic star bursts. Meanwhile, the ejected black holes could seed new structures in the cosmic wilderness, proving that even the darkest, most massive objects are subject to the universe's capricious whims. Future telescopes like the Nancy Grace Roman Space Telescope will hunt for these rogues by their gravitational footprints, while LISA, the Laser Interferometer Space Antenna, aims to detect the gravitational waves from the mergers that launch them. Every discovery peels back another layer of a truth as old as the cosmos. Nothing, not even a supermassive black hole, is too mighty to escape the universe's turbulence. These runaway giants are more than cosmic anomalies. They're reminders that the universe thrives on upheaval, rewriting its own rules in bursts of unimaginable violence. Picture a cosmic ballet where three stars whirl around each other, their gravitational pull sculpting a disk of dust and gas into a shape that defies logic, a twisted, warped structure where planets might form at impossible angles. This is GW Orionis, a triple star system 700 light-years away that's rewriting the rules of planetary birth. Most models assume planet-forming disks orbit neatly around a single star, flat as a vinyl record. But here, the disk is shredded into misaligned rings, like a stack of plates knocked askew by invisible hands. The reason? 3 young stars locked in a gravitational tug of war, each pulling the disk in different directions, creating a celestial whirlpool where chaos and creation collide. ALMA razor-sharp images reveal the stunning aftermath, concentric dust rings tilted at wild angles, some even orbiting perpendicular to the star's orbital plane. This isn't just a curiosity, it's a revolution. If planets can form in such turmoil, it means they might emerge in orbits wildly different from their parent stars, challenging everything we thought we knew about how solar systems evolve. The implications ripple outward. Imagine a world where 3 suns rise and set in a chaotic dance, casting ever-shifting shadows across its surface. Or consider the fate of planets born in these warped disks. Could gravitational kicks from the stars eventually fling them into interstellar space? The real puzzle is how these systems arise at all. Conventional theory suggests multi-star systems form from fragmenting gas clouds that collapse into sibling stars, but keeping their disks stable enough for planets seems nearly impossible. Yet GW Orionis isn't alone. From HD 98800 to GG Tau A, astronomers are finding more of these twisted nurseries, proving that nature has a flair for defying expectations. Some simulations now suggest magnetic fields or turbulent gas flows might stabilize disks long enough for planets to coalesce, even amid stellar rivalry. Others speculate that planets in these systems form faster, their building blocks herded into dense spiral arms by gravitational resonances. What makes this paradox so thrilling isn't just the celestial mechanics, it's the sheer creativity of the cosmos. GW Orionis forces us to confront the messy, improvisational side of planet formation, where perfect alignments are the exception, not the rule. Every warped disk we find is a reminder that the universe doesn't follow blueprints, it experiments, adapting to the chaos it creates. And somewhere in that chaos, amid the tug of 3 stars, new worlds might be taking shape in ways we're only beginning to imagine. Dwarf galaxies should be cosmic fireworks factories, small, dense, and packed with stars that live fast and die young in brilliant supernova explosions. Yet when astronomers tally up these stellar detonations, the numbers don't add up. These tiny galaxies produce only a fraction of the supernovas predicted by their star-forming activity, as if nature forgot to light half the fuses. This isn't just a head-scratcher for theorists, it's a gap in our understanding of how the universe's building blocks, the heavy elements forged in these explosions, spread through space. One clue lies in the type of stars that dominate dwarf galaxies. Unlike massive spirals like the Milky Way, which host a diverse stellar population, dwarfs are often dominated by small, ancient stars that burn slowly and rarely explode. But that doesn't fully explain the deficit. Even accounting for their stellar demographics, models still overpredict supernova rates by as much as 60%. The discrepancy might hinge on a subtle cosmic detail, metallicity, or the abundance of elements heavier than hydrogen and helium. Stars born in metal-poor environments like primordial dwarf galaxies could have fundamentally different life cycles. Their cores might collapse more quietly, forming black holes without the dramatic fireworks we associate with supernovas. Alternatively, their outer layers could be so stripped away by stellar winds that the explosions lack the brightness to detect across vast distances. Then there's the role of environment. Dwarf galaxies often orbit larger hosts, their gas reservoirs stripped away by tidal forces or heated to temperatures too high for efficient star formation. Without fresh gas to birth new stars, the raw material for supernovas dwindles. Some dwarfs might even be quenched, their star formation snuffed out so long ago that the few remaining massive stars have already exploded, leaving behind a silent population of aging suns. This would make them appear anomalously quiet today, despite a potentially violent past. The implications ripple far beyond stellar astronomy. Supernovas are the universe's primary distributors of heavy elements: oxygen, carbon, iron, the very ingredients for planets and life. If dwarf galaxies underproduce these explosions, their surrounding intergalactic medium might remain chemically pristine, like untouched cosmic wilderness. Alternatively, their supernovas could be ejecting elements in ways we don't yet understand. Observations of ultra-faint dwarfs reveal puzzlingly high ratios of certain metals, suggesting that when these galaxies do explode, they might do so more efficiently, enriching their surroundings in concentrated bursts rather than steady waves. Solving this mystery requires peering deeper into these galactic underdogs. Next-generation telescopes like the Vera Rubin Observatory will monitor thousands of dwarfs for rare supernovas, while JWST infrared eyes probe their stellar populations for hidden giants on the verge of collapse. The answer could rewrite our cosmic periodic table, revealing how the smallest galaxies shaped the chemistry of the universe, one quiet explosion or lack thereof at a time. What makes this enigma so compelling isn't just the missing explosions, it's the realization that the universe doesn't play by uniform rules. Dwarf galaxies aren't just scaled-down versions of their larger cousins. They're unique ecosystems where stars live, die, and enrich the cosmos in ways we're only beginning to glimpse. Every undetected supernova is a silent question, urging us to look deeper into the faintest corners of the sky where the most unexpected lessons await. Most stars live quiet lives, steadily burning their fuel over billions of years, but not the luminous blue variables. These celestial divas are the rock stars of the cosmos, prone to violent, unpredictable outbursts that shred the rulebook of stellar evolution. Take Eta Carinae, the most infamous of them all. In 1843, it suddenly flared brighter than Canopus, the second brightest star in Earth's night sky, ejecting enough material to build 3 solar systems before fading back into obscurity. This wasn't just a stellar tantrum, it was a cosmic explosion so powerful it left behind the homunculus nebula, a glowing hourglass of debris expanding at millions of kilometers per hour. What drives such extreme behavior? The answer might lie in a precarious balancing act between gravity and radiation. Luminous blue variables straddle the upper limit of how massive a star can be without tearing itself apart. Some tip the scales at over 150 solar masses. At these extremes, their outer layers become so energized by internal fusion that radiation pressure overcomes gravity, puffing the star up like a balloon until it literally blows off its own surface. But here's the twist: these eruptions aren't random. They may be triggered by a phenomenon called pair instability, where core temperatures soar so high that photons spontaneously convert into electron-positron pairs, robbing the star of internal pressure support. The core collapses, igniting a runaway thermonuclear reaction that rips through the star, but stops just short of a full supernova. The implications are staggering. If these outbursts are failed supernova, they could explain mysterious gaps in the stellar mass spectrum. Normally, supernova leave behind neutron stars or black holes, but pair instability events might vaporize their progenitors completely, leaving nothing but expanding gas clouds. This would solve a long-standing puzzle: why we rarely find remnants of stars in the 150, to 250 solar mass range. Yet the true legacy of luminous blue variables isn't just destruction, it's creation. Their eruptions forge and scatter heavy elements like carbon, oxygen, and nitrogen across interstellar space, seeding future generations of stars and planets with the raw ingredients for life. Eta Carinae alone has ejected 20 times the Sun's mass in such material, a chemical bounty that will someday mix with molecular clouds to form new worlds. The unpredictability of these stars keeps astronomers on high alert. Unlike supernovae, which follow observable precursor signals, LBVs can erupt with little warning. Some, like P Cygni, have undergone multiple outbursts over centuries, while others, like S Doradus, flicker erratically for decades. Monitoring them isn't just academic. A nearby LBV eruption could bathe Earth in harmful radiation, making these celestial time bombs as fascinating as they are formidable. What makes these hypergiants so captivating isn't just their power, it's their defiance. They challenge our neat classifications of stellar life cycles, proving that the universe reserves its most spectacular shows for those willing to live on the edge of stability. Every eruption is both a farewell and a beginning, the death throes of a star, and the birth cry of elements that might one day become part of something new. The Milky Way didn't grow peacefully, it feasted. Scattered across its outer halo, remnants of ancient dwarf galaxies swirl in chaotic orbits, their stars stolen in cosmic collisions that shaped our galaxy's violent past. These stellar survivors should be cosmic breadcrumbs, tracing a predictable path back to their original homes. But there's a problem. Their movements don't match what simulations say they should. Some clump in unexpected arcs, while others race backward against the Milky Way's spin, as if gravity itself forgot the rules. This isn't just a puzzle for galactic archaeologists, it's a challenge to our understanding of how galaxies evolve, and whether dark matter's invisible hand guides the process in ways we've yet to comprehend. Take the Gaia sausage, the butchered remains of a dwarf galaxy that smashed into the Milky Way 8 to 10 billion years ago. When the Gaia spacecraft mapped its stars, researchers expected them to orbit lazily, like debris settling after a car crash. Instead, they found stars hurtling on radial paths straight toward and away from the galactic center, as if the collision sent them ricocheting like billiard balls. This suggests the Milky Way's young disk was far more dynamic than models predict, its gravity warped by a dance of gas, stars, and dark matter we're only beginning to map. Even stranger, the sausage stars are richer in heavy elements than typical halo stars, hinting its progenitor was no ordinary dwarf, but a chemically advanced galaxy that met a violent end. Then there's the Sagittarius dwarf, a galaxy caught in the act of being devoured. As the Milky Way's tides rip it apart, the dwarf has wrapped around our galaxy like a stellar serpent, leaving streams of stars in its wake. But these streams aren't just passive trails, they're kinked and twisted, their shapes betraying the gravitational tug of unseen structures. Some researchers argue these distortions point to dark matter clumps lurking in the halo, invisible wrecking balls perturbing the stream's path. Others propose the Milky Way's dark matter halo isn't smooth, as traditionally assumed, but lumpy, its uneven pull sculpting the debris into these bizarre formations. The stakes go beyond our galaxy. If dwarf mergers don't unfold as simulations predict, it could mean dark matter interacts with itself or ordinary matter in ways our models miss. Some theories suggest dark matter particles might scatter off each other, creating friction that alters how satellite galaxies spiral inward. Others wonder if the Milky Way's dark halo is triaxial, shaped like a cosmic potato, its irregular gravity field deflecting incoming dwarfs onto wilder orbits. Gaia's latest data reveals even more surprises. Stars from long-dead galaxies orbiting perpendicular to the disk, or clustered in vast, rotating planes that shouldn't survive billions of years of galactic turbulence. What makes this horizon so thrilling isn't just the forensic reconstruction of the Milky Way's past, it's the realization that galaxy growth is messier than we imagined. Every stellar stream, every rogue orbit, is a chapter in a story still being written. As next-generation telescopes like the Rubin Observatory and NASA's Nancy Grace Roman Space Telescope join the hunt, they'll expose even fainter threads in this cosmic tapestry, revealing whether our galaxy's appetite follows universal rules, or if every collision writes its own chaotic physics. The Milky Way's halo isn't just a graveyard of lost galaxies. It's a living archive, its stolen stars whispering secrets about the dark, invisible forces that built our cosmic home. Finding exoplanets has become almost routine, thousands detected, some Earth-sized, others orbiting in habitable zones where liquid water could exist. But where are all their moons? In our own solar system, moons outnumber planets by more than 20 to 1, with some like Europa and Enceladus harboring subsurface oceans that might support life. Yet beyond our cosmic neighborhood, not a single confirmed exomoon has been found. This isn't just a case of missing data, it's a glaring cosmic discrepancy that forces us to ask, are moons truly rare around distant worlds, or are we just looking with the wrong tools? The challenge begins with scale. Spotting an exoplanet is like detecting a moth fluttering past a streetlight from miles away. Now imagine that moth has a tiny flea clinging to it. That's the relative size difference between a typical gas giant and its moon. Current telescopes struggle to resolve such minute details, especially when the streetlight, the host star, drowns out faint signals. But astronomers are getting creative. One promising method watches for transit timing variations, tiny hiccups in a planet's orbit caused by the gravitational tug of an unseen moon. Picture a figure skater spinning with a partner. Their combined center of mass shifts slightly, altering the rhythm of their motion. Similarly, a moon's pull can make its host planet arrive early or late during transits, betraying its presence. Then there's microlensing, a cosmic magnifying glass that bends light around massive objects. When a star with planets passes in front of a more distant star, its gravity acts as a lens, briefly brightening the background star's light. A moon orbiting one of those planets could add its own subtle fingerprint to this flare, like a ripple within a ripple. In 2017, astronomers thought they'd caught the first exomoon this way, a Neptune-sized object orbiting a Jupiter-like planet 8,000 light-years away. Dubbed Kepler 1625b, the candidate remains unconfirmed, a tantalizing maybe that underscores how painstaking this hunt truly is. The stakes are higher than just tallying celestial satellites. Exomoons could be the most promising habitats for life in the universe. Consider this: while only a fraction of exoplanets orbit in their star's habitable zone, their moons might. A gas giant parked too close to its star would be scorched, but a large moon at the right distance could enjoy temperate conditions, with tidal heating from the planet's gravity providing extra warmth to maintain liquid water. Our own solar system hints at this possibility. Europa's subsurface ocean is kept liquid not by sunlight, but by Jupiter's relentless gravitational kneading. Upcoming telescopes like the European Extremely Large Telescope and NASA's Nancy Grace Roman Space Telescope will bring sharper eyes to this search. Their advanced optics and sensitivity might finally reveal these hidden worlds, especially around nearby stars like Proxima Centauri, where an Earth-mass exomoon could theoretically orbit its planet in the habitable zone. Some theorists even speculate about exotic moon-planet interactions we've never seen, tides so extreme they trigger volcanic activity, or binary moons sharing an atmosphere. The silence so far isn't necessarily bad news. It could mean moons form differently around other stars, or that our current methods are like fishing with nets too coarse to catch the most interesting fish. But if and when we do confirm that first exomoon, it won't just be a footnote in astronomy, it'll open a new frontier. Suddenly, the number of potential life-bearing worlds in the galaxy could multiply exponentially, with moons becoming not just companions to planets but protagonists in their own right. The hunt continues not just for the sake of discovery, but for the possibility that the best places to find life aren't planets at all, but the worlds orbiting them. Black holes devour everything that crosses their event horizon. But what if the universe has a cosmic reset button? Enter white holes, the hypothetical twins of black holes where nothing can enter, only escape. According to general relativity, if you reverse time in the equations describing a black hole's collapse, you get this bizarre counterpart, a singularity that spews out matter and energy like a cosmic fountain, forever sealed against entry. The idea isn't just mathematical whimsy, it's a radical challenge to how we think about the fate of matter, the direction of time, and even the origins of the universe itself. One of the most provocative theories suggests the Big Bang might have been a white hole event. Instead of a singularity of infinite density, imagine a rupture in space-time where all the universe's energy and matter erupted into existence. This wouldn't just explain the initial explosion, it could redefine what came before. If a white hole represents the time-reversed aftermath of a black hole's formation in some other universe, our entire cosmos might be the aftermath of a gravitational collapse elsewhere. The implications are staggering. The Big Bang wouldn't be the absolute beginning, but a rebirth, a cosmic phoenix rising from the ashes of a predecessor universe's demise. Quantum mechanics adds another layer of intrigue. While classical relativity suggests white holes are eternally stable, quantum effects might allow them to flicker into existence briefly before collapsing into black holes. Some models of loop quantum gravity, which attempts to unify general relativity with quantum theory, predict these short-lived quantum white holes could form when black holes reach the end of their evaporation via Hawking radiation. Picture a black hole shrinking to a critical point, then rebounding in a burst of energy, a final act of defiance against total annihilation. These transient white holes might even explain certain high-energy astrophysical events, like mysterious gamma-ray bursts with no visible source. Yet for all their theoretical appeal, white holes face a glaring problem. We've never observed one. Their very nature makes detection fiendishly difficult. A classical white hole, by definition, emits light and matter but absorbs nothing, meaning we'd only see it if we happen to catch it in the act of eruption. Some astronomers have speculated that unusual objects like the WOW signal or certain fast radio bursts could be white hole signatures, but these remain speculative at best. Others argue that if white holes exist, they'd likely be unstable, collapsing into black holes almost instantly under the weight of their own gravity, leaving only a fleeting window for observation. What makes this hypothesis so compelling isn't just the science fiction allure, it's the philosophical shift it demands. White holes force us to confront the asymmetry of time in our universe. Why do black holes seem so abundant while their time-reversed counterparts remain elusive? Is it a quirk of initial conditions or a deeper law of physics favoring entropy's relentless march? Whether white holes exist or not, their mere possibility stretches our imagination, suggesting that singularities might not always be in points. They could be gateways, cosmic turnstiles between one existence and the next, whispering that even in the darkest corners of physics, there might always be a way out. Zoom in far enough, past atoms, past quarks, down to scales a billionth of a proton size, and the universe stops looking smooth. Here, in the domain of the Planck length, space-time itself might seethe with a frenzied quantum foam, a subatomic froth where tiny black holes flicker in and out of existence, and microscopic wormholes stitch together fleeting connections between distant points. This isn't just empty space, it's a dynamic, probabilistic foam where the very fabric of reality churns like a boiling ocean. Its foam bubbles popping into and out of existence so quickly that even the concept of here and now loses all meaning. The idea traces back to physicist John Wheeler in the 1950s, who proposed that at these unimaginably tiny scales, spacetime's smooth geometry shatters into a chaotic, ever-changing landscape. Picture the surface of a calm lake from a distance. It appears glassy and still, but up close, it's a storm of colliding water molecules. Quantum foam suggests spacetime behaves the same way. Its apparent smoothness an illusion averaged across trillions of these Planck-scale fluctuations. The implications are staggering. If spacetime is fundamentally foamy, it could mean that the vacuum of space isn't empty at all, but a bubbling cauldron of energy that might hold the key to dark energy's mysterious push accelerating the universe's expansion. Some theories propose that this seething foam could allow for something even more radical: natural wormholes. These wouldn't be the stable, traversable tunnels of science fiction, but ephemeral quantum bridges, forming and dissolving in fractions of a second. Under rare conditions, 2 points in spacetime might briefly connect, offering a shortcut across the cosmos. While these wormholes would be far too tiny and unstable for human travel, their existence would rewrite our understanding of causality and locality, proving that space isn't just flexible, it's perforated with hidden threads weaving the universe together in ways we've barely begun to imagine. The hunt for evidence of quantum foam is already underway. Experiments like the Fermi Gamma Ray Space Telescope analyze high-energy photons from distant quasars. If spacetime is foamy, these photons should scatter slightly as they traverse billions of light-years, their wavelength subtly distorted by the froth's turbulence. Other approaches involve ultra-precise atomic clocks, which could detect minute fluctuations in the flow of time caused by spacetime's granularity. Even gravitational wave detectors like LIGO might one day sense the ripples from Planck-scale black holes evaporating into nothingness. What makes this horizon so thrilling isn't just the science, it's the philosophical shift it demands. If quantum foam is real, then the universe we perceive is a kind of cosmic illusion, a smoothed-out projection of something far wilder beneath. Every empty patch of space, every quiet moment, would be a frenzy of creation and annihilation, a reminder that reality's true texture is woven from chaos and connection in equal measure. The foam whispers that even the void is alive, and the answers to our biggest cosmic questions might lie in the spaces between spaces where the fabric of existence is still being stitched together, one Planck-length thread at a time. Our solar system doesn't just orbit the Sun, it's also racing around the Milky Way at over 200 kilometers per second, completing a full circuit every 230 million years. This cosmic lap, known as a galactic year, might seem like a meaningless backdrop to Earth's history until you line it up with the fossil record. Astonishingly, several of our planet's most devastating mass extinctions, including the Permian-Triassic event that wiped out 96% of marine species, appear to recur roughly every 30 to 35 galactic years. The odds of this alignment being pure chance, astronomers calculate less than 2%. Something far bigger than Earth's own cycles may be at play, a celestial metronome ticking in time with life and death on our planet. The prime suspect lies in the Milky Way's spiral arms dense, star-packed regions where gravitational turbulence runs high. As our solar system weaves in and out of these arms during its orbit, it encounters environments that could spell disaster for life below. One theory suggests that passing through these regions disturbs the Oort Cloud, the icy reservoir of comets at our solar system's edge, sending a hail of frozen debris hurtling inward. Evidence comes from impact craters. The Chicxulub crater, linked to the dinosaurs' demise 66 million years ago, coincides with one of these spiral arm crossings. Even more eerily, the late Devonian extinction, which devastated marine life 375 million years ago, aligns with another. It's as if the galaxy itself has a trigger finger and Earth is in its crosshairs. But comets aren't the only threat. Spiral arms are also rife with molecular clouds, vast, cold regions of gas and dust. Some researchers propose that as the sun plows through these clouds, their increased density could compress the heliosphere, the protective magnetic bubble around our solar system, allowing more cosmic rays to penetrate. These high-energy particles might seed low-altitude clouds, triggering global cooling, or directly damage DNA, spurring mutations and biodiversity collapse. Supporting this, ice core records show spikes in radioactive isotopes like iron-60 during past extinctions, traces of nearby supernova more likely in star-rich spiral arms. Yet skeptics point to gaps in the pattern. Not every spiral arm crossing matches a mass extinction, and some catastrophes, like the Triassic-Jurassic event, fall out of sync. Could the correlation be a cosmic coincidence, our brains wired to find patterns even in randomness, or are we missing pieces like the galaxy's vertical oscillations? The Milky Way doesn't just spin. It also bobs up and down through its disk, potentially exposing Earth to the galaxy's high-energy halo or nearby dwarf galaxies' gravitational nudges. The implications stretch beyond paleontology. If galactic rhythms shape life's ebb and flow, then planets in similar orbits around other stars might face cyclical apocalypses. A world in a quiet region of its galaxy could enjoy long stretches of stability, while one perpetually crossing spiral arms might struggle to sustain complex life. Future telescopes like the Vera Rubin Observatory could test this by mapping exoplanet positions relative to their galaxy's structures, hunting for zones where life has the best odds to thrive or perish. What makes this paradox so haunting isn't just the science, it's the scale. The forces that shape life on Earth may not begin on Earth at all, but in the grand choreography of the Milky Way. Every fossil, every crater could be a footnote in a story written across light years, reminding us that biology doesn't unfold in isolation. It's part of a dance far older and vaster than we've ever imagined, one where the galaxy leads and life, for better or worse, must follow. Deep in the constellation Cancer, a planet orbits so close to its star that a single year lasts just 18 hours, a scorching world where temperatures soar above 2,000 degrees Celsius. But 55 Cancri isn't just another blistering hellscape. It's a cosmic jewel box, under pressures 1,000,000 times greater than Earth's surface. This planet's carbon-rich interior may have crystallized into something extraordinary, a lattice of diamonds spanning thousands of miles. Imagine a world where mountains aren't made of rock, but of glittering gemstone, where the very ground beneath your feet, if you could stand on it, would be the ultimate alchemist's dream. This diamond planet's origins read like a celestial recipe gone wild. Most rocky worlds, like Earth, form from silicon and oxygen-rich materials, creating familiar minerals like quartz and feldspar. But 55 Cancri was born in a system with far more carbon than our solar system, a cosmic quirk that reshaped its entire geology. Under the crushing weight of its own atmosphere, so dense some models suggest it's partially vaporized rock, Carbon atoms bond in tetrahedral patterns, forging diamond instead of graphite. The process isn't so different from how diamonds form on Earth, just scaled to planetary insanity. Take a carbon-heavy protoplanet, add unimaginable heat and pressure, and let stellar gravity do the rest. The implications for planetary science are staggering. If diamond worlds exist, what other exotic chemistries might lurk in the cosmos? Planets with mantles of sapphire aluminum oxide, cores of ruby chromium-doped corundum, or even oceans of liquid carbon under diamond icebergs aren't just sci-fi fantasies. They're plausible outcomes of stellar systems with unusual elemental ratios. The universe's periodic table doesn't just create Earth clones. It engineers environments where chemistry follows rules we've barely begun to decode. But here's the real question. Could such a world harbor life? Silicon-based organisms, long theorized as alternatives to our carbon-based biology, might find a foothold in these extreme conditions. On Earth, extremophiles thrive in boiling vents and acid pools. On 55 Cancri, life might evolve in the searing cracks between diamond plates, drawing energy from thermal gradients or chemical reactions between carbon and residual hydrogen. It's a long shot, but the mere possibility forces us to rethink the boundaries of habitability. After all, if life can emerge in the methane seas of Titan or the subsurface oceans of Europa, why not in the glittering depths of a diamond super-Earth? The hunt for these cosmic treasures is just beginning. Telescopes like JWST are analyzing the atmospheres of carbon-rich exoplanets for traces of carbon monoxide or methane chemical fingerprints that could hint at diamond or graphite interiors. Future missions might even detect reflective glints from planetary surfaces, though the extreme heat of worlds like 55 Cancri likely keeps any exposed diamond molten or shrouded in hydrocarbon haze. What makes this horizon so dazzling isn't just the audacity of a diamond planet, it's the reminder that the universe's creativity dwarfs our own. Long before humans prized gems, stars were forging them on scales we're only now learning to measure. Every carbon-rich world is a testament to nature's ingenuity, proving that even the rarest wonders on Earth might be commonplace elsewhere, sparkling evidence that the cosmos never runs out of surprises. The Boot's void isn't just empty, it's a cosmic desert so vast it could swallow 10,000 Milky Ways with room to spare. Stretching 330 million light-years across, this staggering region of near-nothingness defies everything we know about how the universe organizes itself. Galaxies should cluster like cities in the night, bound together by gravity's invisible threads. Yet here, in this yawning chasm of darkness, astronomers have counted fewer than 60 galaxies where thousands should thrive. It's as if someone took an eraser to the cosmos, scrubbing away the stars and leaving behind a blank spot on the celestial map, one that whispers unsettling questions about the universe's hidden architecture. What carved this void? One possibility is as violent as it is invisible: dark energy. This mysterious force accelerating the universe's expansion might have stretched this region thin, pushing galaxies apart until only a sparse skeleton remained. Imagine blowing up a balloon with glitter glued unevenly to its surface. As it inflates, some areas become barren while others clump together. But there's a catch. The Boot's void is too large and too old to fit neatly into standard models of cosmic evolution. Simulations struggle to produce such a colossal emptiness without invoking exotic physics or primordial conditions we've yet to uncover. Then there's the eerie alternative: the void isn't empty at all. The missing galaxies might have merged over eons, their stars consumed by a single supermassive black hole now lurking undetected at the void's heart. Or perhaps the void is filled with dark matter so dense it stifled star formation entirely, leaving behind a shadowy realm of failed galaxies too faint for our telescopes to see. The most radical theory, the Boots void, could be a scar from the universe's birth, a bubble of lower density space frozen into the cosmic fabric during inflation, a fossilized flaw in the Big Bang's aftermath. The implications ripple far beyond this one anomaly. If voids like Boots are more than statistical flukes, they could signal gaps in our understanding of gravity, dark matter, or even the nature of spacetime itself. Future surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time will map millions of galaxies, hunting for other voids and testing whether they align with predictions or demand new physics. Every empty patch of sky isn't just a lack of light. It's a challenge, a cosmic dare to look deeper and question harder. What makes the Boots void so haunting isn't just its emptiness, it's the reminder that absence can be as revealing as presence. In the gaps between galaxies, in the silent stretches where gravity seems to have forgotten its purpose, the universe writes its secrets in negative space. The void isn't a blank page, it's a question mark, one that pushes us to wonder what else might be hidden in the darkness, waiting for the right tools, the right minds to bring it into the light. Black holes dominate our cosmic nightmares, regions where gravity wins so utterly that not even light escapes. But what if there's another way for massive stars to die? Enter the gravastar, a theoretical object so bizarre it makes black holes seem mundane. Picture this: instead of collapsing into a singularity, a dying star's core transforms into an exotic bubble of spacetime, filled with a bizarre quantum soup known as a Bose-Einstein condensate. This isn't just science fiction, it's a radical solution to one of physics' greatest paradoxes: the destruction of information at a black hole's event horizon. The gravastar's secret lies in its layered structure. At its heart, a core of ultra-cold, ultra-dense quantum matter resists further collapse, held up by a form of negative pressure. Surrounding this core is a razor-thin shell of ordinary matter, hovering just above what would have been the event horizon. From the outside, a gravastar might mimic a black hole almost perfectly, warping spacetime, bending light, and devouring nearby matter. But crucially, it lacks that point of no return. Information swallowed by a gravastar wouldn't vanish forever. It would linger at the boundary, preserved in the quantum froth of its interior. This idea didn't emerge from nowhere. Gravastars were proposed in the early 2000s as a way to sidestep the black hole information paradox, the unsettling notion that black holes erase the quantum states of whatever falls in, violating a fundamental tenet of quantum mechanics. If gravastars exist, they'd offer a tidy solution: no singularity, no lost information, just a celestial matryoshka doll hiding quantum secrets beneath its surface. But proving their existence is another matter. Unlike black holes, which leave clear gravitational footprints like the shadow captured by the Event Horizon Telescope, gravastars would be master impersonators, nearly indistinguishable from their more destructive cousins. The real test might come from gravitational waves. When two black holes collide, the resulting ripples in spacetime follow a specific pattern, a crescendo of spiraling frequencies followed by a sharp ring down as the merged object settles. Gravastars, however, could produce subtle deviations, echoes in the signal caused by reflections off their internal structure. Some researchers claim to have spotted these echoes in LIGO data, though the findings remain hotly debated. Others argue that gravastars might be inherently unstable, collapsing into black holes over time, leaving only a brief window for detection. What makes this hypothesis so thrilling isn't just the physics, it's the philosophical shift it demands. Gravastars suggest that even in the face of gravitational oblivion, nature finds a way to preserve order. A dying star wouldn't end as a cosmic eraser, but as a transformer, recycling its collapse into something new and strange. Whether these objects are real or just mathematical phantoms, they remind us that the universe's darkest corners might still hold surprises, places where collapse doesn't mean an end, but a reinvention. Not all galaxies announce themselves with starlight. Drifting through the cosmos like spectral ships, vast clouds of hydrogen gas spin and clump with all the hallmarks of a galaxy, yet they glow with no stars to illuminate them. These are the dark galaxies, cosmic enigmas that challenge our most basic assumptions about how matter organizes itself in the universe. First detected as subtle ripples in radio telescope data, these shadowy structures contain enough gas to birth billions of stars, yet for reasons we don't yet understand, they've remained almost entirely barren. The leading theory suggests these could be galaxies where dark matter won, overwhelmingly dominating the system's gravity to such a degree that ordinary matter never coalesced into stars. Picture a galactic-scale tug-of-war. In typical galaxies like our Milky Way, gas clouds collapse under their own gravity, igniting stars that light up the darkness. But in dark galaxies, the gravitational pull from unseen dark matter might be so diffuse or misaligned that gas never reaches the critical density needed to spark stellar fires. Simulations show that in certain dark matter halos, particularly those with low concentrations or unusual spin, gas could remain too hot or turbulent to form stars, leaving behind a galaxy-sized cloud frozen in embryonic state. Yet there's another possibility, even more intriguing. Some of these objects might not be failed galaxies at all, but intergalactic debris, remnants of violent collisions where entire galaxies were torn apart, their gas stripped away and left to wander as orphan clouds. The Smith Cloud, a massive hydrogen stream hurtling toward the Milky Way, could be a nearby example of such a relic. Unlike dark galaxies, these tidal dwarfs would lack dark matter entirely, their motions governed solely by the gravity of visible gas. Telling the difference hinges on precise measurements of their mass. If these clouds weigh far more than their gas suggests, dark matter is likely pulling the strings. If not, they're probably shredded fragments of past cosmic crashes. The hunt for these phantoms is pushing telescope technology to its limits. Instruments like the Square Kilometre Array, set to come online in the late 2020s, will scan the skies with unprecedented sensitivity, mapping hydrogen's faint radio whispers across billions of light years. Already, projects like the Arecibo Legacy Fast Alpha Survey have uncovered candidates like Dragonfly 44, a galaxy with the mass of the Milky Way but only 1% of its starlight. Its stars are so sparse you could fly a spaceship through it for years without seeing one, yet its gravity betrays the presence of something massive and unseen. What makes dark galaxies so transformative isn't just their existence, it's the realization that our cosmic census has been skewed toward the luminous. For every glittering spiral we've catalogued, there could be dozens of these shadow counterparts, invisible threads in the universe's grand tapestry. They remind us that darkness isn't empty, it's a canvas hiding structures we're only beginning to trace, where the rules of star formation and galactic evolution might play out in ways we've never imagined. The night sky's true richness may lie not in the stars we see, but in the ghosts we've yet to find. Neutron stars are nature's perfect spheres, or so we thought. These stellar corpses, packing more mass than the sun into a city-sized ball, spin so fast their surfaces should be smoother than a mirror, polished by gravity's relentless pull. Yet lurking beneath their crushing gravity and magnetic fields might be the universe's most extreme mountains, not towering peaks, but bumps barely centimeters high. On Earth, that wouldn't even register as a speed bump. but on a neutron star where a teaspoon of material weighs 1 billion tons, these tiny imperfections defy the very limits of physics. How does anything resist gravity this intense? The answer lies in neutron stars' unimaginably dense crusts, a lattice of atomic nuclei squeezed so tightly they form a crystalline shell harder than diamond. Under normal circumstances, this crust should be flawlessly smooth, but magnetic fields billions of times stronger than Earth's can warp it like taffy, creating ridges and valleys as they twist and snap. Picture the star's surface as a frozen lake, its icy surface fractured by pressure from below. Now replace the ice with nuclear matter and the pressure with magnetic forces capable of bending space-time itself. The result, microscopic mountains born from cosmic violence. Accretion adds another layer of chaos. When a neutron star siphons gas from a companion star, the incoming material doesn't land gently. It slams into the surface at near light speeds, creating hotspots of deformation. Over time, these impacts can build up asymmetrical bulges, like cosmic sediment settling unevenly on an impossibly dense shore. Some models suggest these mounds might reach several centimeters tall, enough to disrupt the star's perfect balance. As the star spins, these minuscule bumps generate ripples in space-time called gravitational waves, faint whispers that detectors like LIGO hope to one day trace back to their origins. But the real surprise isn't that these mountains exist, it's what they reveal about the fabric of reality. Neutron star crusts are the strongest material in the known universe, a nuclear pasta where protons and neutrons arrange themselves into shapes resembling spaghetti or lasagna sheets under extreme pressure. The fact that even these structures can deform tells us something profound. There's no such thing as perfection in nature. Every object, no matter how dense or pristine, carries scars from its past, whether it's the gravitational memory of a long-dead star's collapse or the lingering imprint of a magnetic field's fury. Studying these imperfections isn't just about mapping alien landscapes. It's a stress test for the laws of physics. By measuring how neutron star crusts bend and break, we're probing the absolute limits of how matter behaves under conditions impossible to recreate on Earth. Each tiny mountain is a clue, a fingerprint left behind by forces so extreme they warp the very rules we thought governed the universe. And if we're lucky, the next generation of gravitational wave observatories might catch these stars trembling under their own weight, proof that even in the coldest, densest corners of the cosmos, nothing is ever perfectly still. Before the first galaxies, before even the first heavy elements, the universe was a silent expanse of hydrogen and helium, until gravity began sculpting these raw ingredients into something extraordinary. These were the population 3 stars, the cosmic pioneers forged from pure primordial gas, their existence predicted by theory but never yet seen. Unlike modern stars enriched with carbon, oxygen, and iron, these titans were elemental purity incarnate, burning hotter and brighter than anything that would follow. Their birth marked the moment the universe transitioned from darkness to light, igniting the cosmic dawn that would eventually lead to everything we know: planets, life, even the atoms in our bodies. The hunt for these elusive first stars hinges on their unique life cycle. Without heavy elements to help them shed heat, population 3 stars likely grew to staggering sizes, some possibly hundreds of times more massive than our Sun. Such behemoths would have lived fast and died violently, collapsing in supernovae so powerful they seeded the cosmos with the first heavy elements. But spotting their light directly is nearly impossible. Their era ended over 13 billion years ago, their individual glow long since stretched into undetectable infrared by the universe's expansion. Instead, astronomers are searching for their fingerprints' chemical signatures in ancient gas clouds or the afterglow of their explosive deaths. This is where the James Webb Space Telescope becomes our time machine. By peering into the infrared with unprecedented sensitivity, JWST could detect the telltale remnants of population, 3 supernova explosions rich in pair instability events, where stars obliterate themselves without leaving behind black holes. These blasts would have scattered elements like carbon and oxygen in distinct ratios, leaving a chemical trail in the spectra of the earliest galaxies. Even more tantalizing, some models suggest these stars might have formed in isolation, their light too faint to see individually but collectively responsible for lifting the universe's primordial fog during the epoch of reionization. The implications of finding them stretch beyond stellar archaeology. Population 3 stars were the universe's first alchemists, transforming hydrogen and helium into the building blocks of planets and life. Their deaths forged the first heavy elements, which then seeded second-generation stars smaller, longer-lived, and eventually hospitable to planetary systems like ours. If JWST or future telescopes like the Nancy Grace Roman Space Telescope catch a glimpse of their aftermath, it wouldn't just confirm a theory, it would reveal the exact moment the cosmos transitioned from simplicity to complexity, from a monotonous sea of gas to a diverse chemical playground. What makes this search so profound isn't just the science, it's the poetry of connecting our existence to these primordial giants. Every atom in our bodies, every molecule in Earth's crust, was once fused in the hearts of stars. But the very first of those stars were unlike any since, born in a universe so young and pristine we can scarcely imagine it. Their light may be gone, but their legacy is written in everything we see, and with each new observation, we're one step closer to meeting our cosmic ancestors. The cosmic microwave background, the afterglow of the Big Bang, has long been our most pristine window into the universe's infancy. But what if this ancient light holds more than just the secrets of our own cosmos? Hidden within its subtle temperature fluctuations might be the faintest fingerprints of something far stranger, collisions with other universes. This isn't science fiction, it's a frontier hypothesis that pushes the boundaries of cosmology, suggesting that our universe might be just one bubble in an infinite multiverse, and that its neighbors could have left tangible scars on the fabric of reality itself. The idea hinges on a phenomenon called bubble nucleation. Imagine the multiverse as a frothing sea of space-time foam, where each bubble is a self-contained universe with its own unique physics. When these bubbles collide, the impact could send shockwaves rippling through both universes, imprinting circular patterns in their respective cosmic microwave backgrounds. These bruises would appear as concentric rings of temperature variation, slightly warmer or cooler than their surroundings, like ripples frozen in time from a primordial splash. Researchers scanning CMB data from missions like Planck have identified several candidate anomalies, including a particularly intriguing cold spot in the constellation Eridanus, where the temperature dips just enough to raise eyebrows. Could this be the cosmic equivalent of a dent left by another universe bumping into ours? Skeptics argue these patterns could easily be statistical flukes or artifacts of foreground interference. After all, the CMB is a tapestry woven from countless overlapping signals: galactic dust, gravitational lensing, even the Doppler shift from our own motion through space. Teasing out a genuine multiverse signature requires sifting through this noise with near impossible precision. But proponents counter that the specific geometry of these anomalies, their sharp edges and concentric symmetry, sets them apart from random fluctuations. Simulations of universe collisions predict exactly this kind of crisp, circular imprint, a fingerprint that conventional astrophysics struggles to replicate. The implications are staggering. If verified, these marks would be the first empirical evidence of realities beyond our own, proving that existence isn't confined to a single space-time continuum. It would mean our universe isn't just expanding, it's rubbing shoulders with unseen neighbors, each operating under different physical laws. Some theories suggest these collisions could even seed exotic structures within our own cosmos, like the mysterious cosmic voids or unexplained large-scale flows of galaxy clusters that defy standard models. The hunt for these multiverse imprints is far from over. Next-generation CMB experiments like the Simons Observatory and CMB S4 will map the sky's microwave glow with unprecedented resolution, hunting for patterns too subtle for current telescopes to catch. Others are developing algorithms to distinguish true collision signatures from mimics, training artificial intelligence to spot the telltale geometry of a universe-sized impact crater. What makes this search so electrifying isn't just the prospect of finding evidence for other worlds, it's the realization that the ultimate horizon of discovery might not lie in the farthest reaches of space, but in the hidden dimensions brushing up against our own. Every anomalous circle in the CMB is a potential message from beyond the edge of existence, waiting to be decoded. Whether these marks are cosmic mirages or groundbreaking discoveries, their very possibility reshapes how we see our place in the grand scheme of things. The universe has always been larger than we imagined, first beyond Earth, then beyond the Milky Way, then beyond the observable cosmos. Now we're peering over the edge of reality itself, searching for echoes from the other side. And if we find them, it won't just rewrite textbooks, it'll redefine what it means to be part of existence at all.